Okay, can you see the presentation?
Yes, it's okay.
Yes.
So let's start. Welcome everybody. We are very pleased to have this second event on new trends in quantum field theory, amplitudes and gravity. The first one was held at El Colegio Nacional just before the start of the epidemic, and in Mexico City at the Colegio Nacional. Now we have this event online, and I'm very glad that we can have this meeting again. And I want to thank everybody for participating, and to the speakers, and especially to Bern and Lance Dixon that have motivated us to keep. And so we have very interesting talks today, and but just let me say a few words in general about the field. And actually, I'm going to use exactly the same material that I prepared for last year. So it's the following, especially for the students. So quantum field theory is almost 100 years old. It started with the work of Heisenberg, Pauli, Jordan, Dirac, and it combines quantum mechanics and special relativity. Despite the initial worries about the infinities, it was possible to handle them, and this was done by Feynman, Schwinger, Tomonaga, and Dyson too. Play an important role. So they made quantum electrodynamics the first successful quantum field theory. Now, these days, we know that the standard model is our best quantum field theory. It describes nature. It describes the fundamental constituents of matter, quarks and leptons, and the interactions, electroweak and the strong ones. And we all know that the standard model was confirmed with the discovery of the Higgs boson at the LHC in 2012. In order to describe the phenomena of the standard model at the Large Hadron Collider, including the properties of the Higgs particle, we need very complicated calculations for backgrounds, for quantum chromodynamics, and the techniques that we learn from our textbooks, where we start with quantum field theory, those are not enough to handle the complexity of the phenomenon that needs to be described. But we are lucky that the new techniques in quantum field theory have been developed since the 80s and 90s, and they are very powerful, and we have learned a lot. We have developed techniques to make these calculations, multi-particles, and higher orders too. So we can say that we have almost a new field that is being developed these years. And despite the practical applications of quantum field theory, we also have theoretical issues, and it's also very nice that thanks to these new techniques, there has been progress in understanding and having some control of the domain of perturbative quantum gravity, both in pure general relativity and also in supergravity. So we hear now in the papers this term like maximal helicity violation, unitarity cuts, KLT relations, BCFW relations, double copy, amplitude hedron, bootstrapping. These are new terms that we look at the papers these days. So these are very nice topics. As I said, it has applications for real life, collider physics, and also for very interesting theoretical issues. So the idea of this workshop is to take a look into what is going on in this field and motivate the young students to look into these topics. So I hope that they will be motivated to start to work in these very nice subjects. So our meeting today is only one day, and we'll have very nice, very interesting talks. We start first with Lance Dixon, that will talk about amplitudes and N=4 super Young-Mills theory. That was like a provisional title, so we will hear from him what will be the more precise title. The next session in the morning will be by Lucia Cordova, who works as a postdoc in France, and she will talk about symmetric bootstrap and the space of quantum field theory. That will be the session in the morning. And then we'll have a break for lunch, and we'll return at 3 p.m. for the talk by Bern on amplitudes and gravity. Next, we'll have a talk by Professor Alfredo Guevara from Chile, who is now at Harvard, and it will deal with the quantum field theory, scattering waves in Kerr. We'll have a coffee break. Everybody at home, choose your own espresso machine and have a nice coffee. And we'll close the session with a talk by Andres Luna of aspects of classical double copy. So again, welcome everybody. I hope that everybody will get will have many questions to the speakers. So this is all that I have to say. Welcome everybody, and many thanks to the speakers that very kindly accepted to talk today. So we have like 7 minutes. Just relax and let's prepare for the next the first talk by Professor Lance Dixon from SLAC. And so we wait 5 minutes to start. First talk, we have very pleased to have Lance Dixon. He's one of the persons that has contributed mostly to this field. He's, as I said, he's a professor at SLAC, and he will talk about amplitudes in planar N=4 super Young-Mills theory.
Thank you very much, Lorenzo, and to everyone who put together this nice symposium today. It's a great pleasure and honor to be able to speak here. And indeed, I'm going to tell you something about some modern methods for calculating amplitudes in planar N=4 super Yang-Mills theory. This theory is not the real world, but it has some things related to theories in the real world. And I wanted to start off by just setting the context a little bit for why we're interested in scattering amplitudes in similar theories, like quantum chromodynamics. And for me, at least, a lot of the motivation for this has to do with the ability to explore matter and particle interactions at the shortest distances possible. And in the modern era, the energy frontier, where you can do these explorations at the very shortest distances by having the highest energy collisions, that frontier has been at hadron colliders. The Fermilab Tevatron collided protons and antiprotons at 2 teravolts. And then the baton was passed in around 2010 to the Large Hadron Collider at CERN near Geneva, Switzerland. You can see some of Geneva, you can see the airport on the right and Lake Geneva in the background. And this ring is 27 kilometers around, and it has a number of different experiments, especially ATLAS and CMS, which look at the highest energy collisions. The shortest distances are what they call high PT, high transverse momentum collisions. And here's a few of those collisions. There are trillions of proton-proton collisions at the LHC. Most of them, the protons just tickle each other a little bit. They could break up and leave a little splat along the detector, but these are like among the most violent events. And some of them produced the Higgs boson, which, as Lorenzo mentioned, was discovered almost 10 years ago now in 2012. And it's continuing to be explored at the LHC. The LHC is coming back from a shutdown, and it will run for about 3 years. Then it will shut down again for a few years while they prepare for the highest luminosity runs. And the events that you can see that contain a Higgs boson, well, there's a lot of background, so it's not always completely obvious which events are Higgs's, but this event is consistent with a Higgs decaying to 2 photons. These green segments here are photons that were detected in a part of the CMS detector called the calorimeter, and there was no track pointing to them. So the neutral object came in and then made a splat, a shower that looks like a photon. And this mass is consistent with the Higgs. But it could have been a background event. It's only when you add up all the events that you see that there was a Higgs that decayed to 2 photons by summing up many events. This event over here is much cleaner. These 4 red lines denote particles that were left a very small track in the tracking detector in the inside, and then some more tracks way outside where no hadrons could penetrate, no strongly interacting particles could penetrate. Those are muons. And there are a handful of events with 4 muons whose mass adds up to the Higgs boson mass of 125 GeV. And these guys are quite clean. There's very little background for this. Then there are events that seem to have nothing to do with the Higgs, but are just produced by the standard model. And this is one of the most violent events. That is, it has 2 jets, which are probably quarks, coming out of the central collision. And if you work out their invariant mass, it's 8 TeV. And that was out of a total of 13 TeV possible in the collision. So that means that these quarks were each carrying most of the momentum of the proton, which is rather incredible. It's a very low probability for that to happen, but there are trillions of events. And then you can have much more complicated events where you don't produce just 1 particle or 2 jets, but like 6 jets here, or TT bar, each of which decays to 3 jets or 1 jet and a W. So you can get extremely complicated events. And that means there's a lot of premium on doing calculations for all of these different event rates to as high an accuracy as you can to compare with the experimental accuracy. Here's a theorist picture from Frank Krauss of a typical LHC event that has 2 protons colliding, recognizing that the protons are bags of quarks and gluons. And in the middle of the collision, we call this the short distance interaction. Now it's a little ambiguous what's the short distance part, but roughly it's in there. And this might have produced a Higgs, maybe that decayed to 2 B quarks or something, but there are many different options here. And the long distance part of the collision is very complicated and needs to be modeled in a certain way. You have to know the structure of the proton, which we know quite well. You have to know how these quarks and gluons, which often split and branch in a collinear fashion. This part you know semi-well. And then when you get out here, this is a very a model where you sort of parameterize how the quarks and gluons turn into the strongly interacting particles, pions, kaons, protons. that actually reach the detector. So it's very complicated. And this outer part is hard because the quantum chromodynamics is a confining theory, and it's very strongly coupled at long distances, which is on the outside or low Q. By the way,
can I?
Yes, please. I meant to say.
A question, yes.
Please ask.
So in this picture, what is a jet? So which one of these is identified as a jet?
So first of all, there are different jet algorithms, and you can vary things. So it's not always unambiguous. But roughly speaking, a jet is a cluster of energy that's close in space in the detector. So you make a cut, a circle roughly. This is very rough. You make a circle which has a certain radius in azimuthal angle and in polar angle, but you usually use a better variable called the rapidity. That's better boost properties. But roughly speaking, jets should correspond to partons that were produced at short distances. So you look here and you trace the stuff that comes from it, and it would often be in the same jet, but it could emerge in another jet. So this Higgs boson decays into a B and an anti-B. Normally, those would be separate jets. But if the Higgs were produced with very high momentum, those two would be very close to each other, and they might be in the same jet. So some techniques, you start with a broad jet definition that finds one jet, and then you look inside it and look for two jets. So, then you use both aspects to find the Higgs. That's a technique to try to find the Higgs decaying to BB bar. It's called boosted jets. So yeah, there are different ways to define jets, but roughly speaking, they should correspond to a quark or a gluon from the short distance collision. Any other questions? So there's a range of scales in this collision and in this problem. And as I was saying, the outside part is very hard to compute. You more or less have to model this part of it, and this part you take from experiment. But in the inside here, the nonlinearities are small. That is, the coupling constant is small. The strong coupling, it runs. It's asymptotically free, as was discovered by Gross and Wilczek and Politzer in the early 70s. And at the scales of these typical collisions, which in momentum space is about 100 GeV, it's about a tenth. So you can calculate using perturbation theory, order by order in the strong coupling. And there's a factorization picture which sort of corresponds to the previous one, which we sample when we're at very short distances, the odds of two different partons, quarks or gluons, coming out of the proton is small. You mostly just see one at a time. And so you need a probability distribution here, which is called a PDF, or parton distribution function. So there's a mathematical description of this red blob. And then you multiply those probabilities together, and you also multiply them by a quantity called the short distance cross section. And that's sort of where West theorists who do perturbation theory operate, inside this box, inside this femto universe. And this box, you can change the size of the box, and this changes, and these things change a little bit, but they compensate. And the product is roughly invariant. We call that factorization scale invariance. So we calculate these pieces using perturbative QCD. And so it's an expansion in alpha S. Often it's written as alpha S over pi or alpha S over 2 pi or something. And the leading term, depending on the process, might actually have some powers of alpha S in it too. So there's some integer here. And then you need to calculate these coefficients. And this one just comes from drawing tree level Feynman diagrams and squaring them. This one will have loop level Feynman diagrams and also trees with one more leg, one more gluon or quark in the final state. And this will have 2 loop and other stuff. And the issue is that these coefficients are very big. And so the series does not converge very quickly. And it depends on the process. And this is one of the worst processes in terms of how long it takes to converge. And this process shown here is the cross-section in picobarns for producing the Higgs boson at the LHC. Now the LHC has run at different energies, 8 and 13, and it's going to start running at 14 in the next run. And the cross-section goes up with energy, basically because you get to use gluons that fuse to form the Higgs that have lower momentum, and there are more gluons at lower momentum when you raise the beam energy. That's why the cross-sections always go up when you increase the energy at a hadron collider. So, but to know exactly how big the cross-section is at each energy, you have to calculate order by order in perturbation theory. And the leading order result has some estimate of its error, which is totally wrong. Because when you do the next calculation, you see it jumps by almost a factor of 2. And then that error estimate also turns out to be not that great. And that the next order, NNLO, it jumps up to the upper edge of that. And then finally, when you get to NNLO, it looks like it's more or less settling down because this band is kind of in the middle of the previous band. So this error estimate is likely to be quite reliable. But all these orders in perturbation theory for this process resulted in a huge increase. And if you try to make a measurement of the Higgs, any measurement you make sort of relies, the interpretation of it relies on this cross-section to know how many were produced. Technically, this is the gluon fusion cross-section, and there are other cross-sections that you can produce the Higgs by, but this is the biggest one, and it was also the biggest theoretical challenge too. So you need good precision here because the experiments are going to measure things with similar precision to this in the high luminosity LHC run. Any questions about that? Now, without going into any details at all of these calculations of these higher order cross sections at the LHC, they have underlying them as sort of an engine scattering amplitudes or S matrix elements that you need to combine to make the cross sections. And each of these S matrix elements for individual numbers of final states is actually divergent. It's infrared divergent. But when you combine them all in the right way, you get a finite answer, which you can hand to the experimentalists. I just wanted to mention that there's been a lot of progress in the past decades in trying to make these calculations more accurate. You already saw the progress in improving the Higgs precision. There's also progress in broadening the predictions to more and more different processes. And in the beginning, that was kind of slow. So the first calculations of producing the Higgs, or maybe in this day, a W boson or a Z boson at a hadron collider, that's 2 goes to 1 because you have 2 quarks in and 1 particle out, like the Higgs or a vector boson. So that was sort of done in 1980. But to do 2 goes to 2, it was almost 1990. And it was almost 2000 by the time people did 2 goes to 3. But then in the late 2000s and early 2010s, new technology came along for calculating 1 loop amplitudes, which you need for NLO, with many legs. And then it was possible to do 2 goes to 4, 2 goes to 5, and 2 goes to 6. And so there was a lot of progress, and a lot of this has also been incorporated into more realistic Monte Carlo generators by now in supplying next to leading order results for a lot of standard model and beyond the standard model processes that the experimentalists can compare to their measurements. Now, NNLO, to try to make it for a broad set of processes, has been a much bigger challenge. And so 2 goes to 2 was sort of done several years ago, but 2 goes to 3 has been a bottleneck. And the first high rate process for 2 goes to 3 was the amplitudes for it, not the full cross section, but just those S matrix amplitudes were done just last year. by a collaboration that included, for example, Fernando Febres Cordero and Harold Ida, who had worked with, we worked with them, Svi and I and others in the one loop, and now they're extending these kinds of techniques and generalizing them and making them more sophisticated for the two loop case. But this is sort of the state of the art for two loops. 2 goes to 2 is more or less under control, but 2 goes to 3 is the frontier. Any questions about that so far? I wanted to make a big distinction between NLO and NNLO. When you have
yes, sorry.
Go ahead, Andre.
Yes, before moving to that,
yeah.
Can you say a bit about the going from amplitude to cross section? Is that difficult or?
Yes, it's very difficult.
So, yeah.
I mean, it would be a whole lecture in itself. But basically, the individual contributions with different numbers of particles in the final state are not finite separately, and they have to be combined in a certain way. Maybe you had a quantum field theory course for QED where you learned that an electron never really exists in isolation. It always has a cloud of soft photons around it. If you try to insist that there are no soft photons at all, you will get 0 probability of the reaction, because there is always, if you make the energy of the photon low enough, the probability of that photon being there diverges, goes to infinity. We call that a soft divergence. So in QCD, there are also collinear divergences, because you sort of don't observe quarks directly, and quarks can split into gluons and give up lots of their momentum when the gluon is collinear. And that forms a jet, but you have to take that collinear stuff into account and define a jet properly. And these real divergences, they always cancel against virtual loops. So that you have a collinear divergence of a real emission can cancel against a virtual collinear splitting, where that gluon is virtual and reabsorbed. But the real headache for people doing these extra steps is that these phase space configurations are very complicated. When you have many additional radiated particles, you have triple collinear singularities, soft times collinear, double soft, double collinear in 2 different regions. You have to keep track of all of these, and you have to find algorithms that remove the divergences but allow you to do things very flexibly, because the experimental cuts, you don't know exactly what they're going to be, or they're very strange. So it's a long song and dance.
Yep.
That would take a long time to describe more than that.
Okay. Yes. Thanks.
That's probably enough for you anyway.
Yeah.
Any other questions? Okay. So the big issue when you go from NLO to NNLO, besides these real radiation effects, is that 2-loop integrals are much more complicated in general than 1-loop integrals. 1-loop integrals, when all the particles are in 4 space-time dimensions, you can show that they all reduce to scalar box integrals or something simpler. And way back in 1974, maybe even earlier, 't Hooft and Veltman, I mean, other people knew aspects of this earlier, knew that these were all dilogarithms. So there's like only one special function you need to know. The dilogarithm is the integral of a logarithm. This is actually dt over 1 minus t, roughly. So you do one kind of logarithmic integration, and then you do another kind of logarithmic integration. And that transcendental function is the most complicated function you need at 1 loop. And we're going to talk about things that are relevant for 2 and higher loops that are generalizations of these dilogarithms, but they're quite a bit trickier. And to try to simplify things and focus on these transcendental functions, we're going to change the theory now. So we're going to leave the real world, and we're going to go to an idealized gauge theory, which is very nice theoretically. And it has a lot of relations to QCD, but it's not QCD. And this is planar n equals 4 super-Yang-Mills theory. So QCD contains a gluon. So does this theory. And the gauge group for QCD is SU3. Here we're going to leave NC arbitrary. Well, actually, we're going to take it very large. NC goes to infinity. Atuf described this as the planar limit because he realized that planar Feynman diagrams dominate in that limit. So we have gluons. We also have fermions. In QCD, the fermions are quarks, and you can have different numbers of quarks, up, down, strange, charm, top, bottom. Here we have particles which are not quarks. They're called gluinos. They're in the adjoint representation of this gauge group, whereas quarks would be in the fundamental. And to have n equals 4 supersymmetry, we should have exactly 4 of these. Each one corresponds to a supersymmetry rotation in a slightly different direction from the spin 1 gluon. And when you keep applying more supersymmetry generators, you also generate 6 massless spin 0 scalars. So you apply 4 supercharges to a gluon of, say, plus helicity, and you get gluinos of plus 1/2 helicity. And you, because supersymmetry always changes the spin, or in this case, the helicity, by 1/2. And you do it again, you get to the scalars. You do it again, you get helicity minus 1/2. And there are only 4 at this time because of the q squared. An individual q squares to 0. So you only get antisymmetric combinations of these q's. And the most you can get is 4 antisymmetric combinations. And that leaves you with a helicity that goes from 1 down by 1/2 4 times to -1. And this is the maximal supersymmetry you can have, where the spin is at most 1. If you have more supersymmetry, you need at least spin 3/2, and we don't know how to make that consistent unless you also have spin 2 and supergravity. So this is the best you can do kind of without gravity, the most symmetric theory. And it has lots of amazing properties, especially it becomes even more amazing if you take the limit NC goes to infinity, the number of colors to be infinite. And that's what we call planar n equals 4. Any questions about that? Okay, so this is a toy model for QCD amplitudes. And I mean, a general amplitude in a theory, just kind of the way functions can be described, is that you can have rational functions, and then you can have more complicated functions, which we'll just call transcendental. And the general function of the kinematics, like an amplitude, might be a sum of different rational terms and different transcendental terms. But in the n equals 4 case, I'm not going to go into the details, but we understand this rational structure very well. And so it's more of a question of what are the transcendental functions doing? And so I'm going to focus on the transcendental functions in this talk. So the space of functions also turns out to be so restrictive, and the physical constraints that we have on them are so powerful that we can do a bootstrap procedure. Now, in the next talk, Lucia is going to talk about bootstrapping, but it's a different philosophy, I would say. This is trying to determine exact forms of amplitudes in a very specific theory, whereas what she's going to talk about is general constraints on the space of theories. So it's a slightly different philosophy. And this bootstrap is more perturbative, and she's going to be discussing things that are more non-perturbative. And this bootstrap requires having some idea of what the function space looks like. And in our case, from experience at low loop orders, we kind of know that the answers, we suspect that the answers are going to be certain functions called polylogarithms, which are generalizations of the dilogarithm we talked about earlier. And if we think we know the right function space, we can just write the answer as a linear combination of those functions. And then if we have enough constraints, we could fix all of the unknown linear constants. And so at the end of the day, the work we are doing is solving linear constraints. So you reduce everything to a problem in linear algebra. This is a picture of what we understand generically about scattering in planar n equals 4 super Yang-Mills. The picture has 2 axes. This axis is literally the coupling constant in the theory. So there's a coupling like alpha S, the Yang-Mills coupling squared, but it gets multiplied by the number of colors because we're taking the number of colors to infinity and holding this constant fixed, which is sometimes called the 't Hooft coupling, lambda. So this is literally the coupling in the vertical direction. In the horizontal direction, there's the kinematical variables. Now, in practice, there are several kinematical variables, but there is one limit, a collinear limit, which you take a certain variable to 0, where we actually have a non-perturbative description. And Lucia was one of the ones contributing to that description. Also, Benjamin Basso, Amit Sever, and Pedro Vieira. So they provided a integrable finite coupling description of this limit, which is based on excitations that go between two edges, and they're called flux tubes. And so the bottom line from my point of view is that we know this boundary condition extremely well. And we can use that information to give us the constraints that we need if we have a good idea of what the function space is. And so the goal here is to build up perturbative information here. But there's another limit that's known as well, and that is in the very strong coupling limit, there's a ADS CFT dual description in terms of a string moving in anti-de Sitter space. And that string sweeps out a surface, and that surface should have a minimal area. And so there's a problem of calculating this minimal area surface, and that problem has an integrability to it too, a classical integrability, whereas this is a quantum integrability, but they're not unrelated. So anyway, we can work out, if we need to, the answers for generic kinematics at strong coupling. So we have the problem all boxed in. We know 3 of the 4 edges, although this isn't really a 2-dimensional picture. But still, the idea is that we would love to be able to do this for arbitrary coupling and arbitrary kinematics. So this is the holy grail of sort of solve what it means to solve scattering in this theory. And we can come in from various angles. That's sort of the big picture of what we're interested in this theory, or what I'm interested in anyway. Any questions about that?
Yes, Lance,
Yep.
what will be this Holy Grail? What it represents?
Well, what would be great is if you could understand the function spaces that I'm going to talk about later, order by order and perturbation theory. They're essentially the same function space. I mean, the different pieces of them contain the different loop calculations. So you would like to understand if there's a well-defined sense in which the finite coupling function is a well-defined mathematical function, or at least one that you can give an algorithm for computing, not just order by order and perturbation theory, but at finite coupling in any kinematics.
Okay.
We don't know for sure what these functions are, but they would be analogs of multivariable hypergeometric functions, something like that.
Okay, thank you.
So just to sketch how things were done for perturbative calculations in the old days, in the early days of quantum field theory that Lorenzo referred back to. For example, the first calculation of the G-2 of the electron by Julian Schwinger. Well, he didn't actually draw Feynman diagrams. He had his own methods, but he did analogous things. But the idea soon after was to draw all Feynman diagrams. And then for each Feynman diagram, you would use the Feynman rules to evaluate them in terms of loop momenta. And then you would have to integrate over the loop momenta or evaluate the loop integrals. And then when you added up all the diagrams, you would get the amplitude. And then with Zvi and David Kossauer and David Dunbar, we proposed using a different method to determine the loop integrand, using unitarity or generalized unitarity. And that has sort of been codified in a lot of these NLO techniques and some of the NNLO techniques as well. But in those methods, you still have to construct the loop integrand and then evaluate the loop integrals. In some cases, like planar n equals 4, there's another even shorter shortcut where you bootstrap. Instead of determining the loop integrand, you sort of write down all possible loop integrals, these functions I was talking about, and then you apply constraints in order to figure out which is the right linear combination of them that corresponds to the amplitude. Of course, you should probably have some checks that you things that have to work that once you've determined the answer uniquely to make sure it's right. But we usually have those. So this method has been applied successfully over the last decade. And the prime example for it has been the 6-gluon amplitude. There are certain symmetries of planar n equals 4, which cause the 4-gluon and 5-gluon amplitudes to be rather trivial in that theory. They don't have any kinematic dependence because of a symmetry called dual conformal symmetry. Anyway, so the first non-trivial one is for 6-gluons. And by making use of a lot of properties of the amplitudes in this theory, we could push this all the way up to 7 loops. So here's a blob representing the scattering of 6-gluons with planar Feynman diagrams, which have 7 loops. Here's one of them, but there are about 1 billion more, although I couldn't really count them all successfully. I tried. Anyway, we can work out what these amplitudes are through 7 loops because the system is so constrained. But this theory, it has these 4 extra symmetries I just mentioned, dual conformal symmetry. And for the 6-gluon amplitude, it means that the thing we compute, the non-trivial part, depends on 4 fewer variables than in QCD. It depends on 3 kinematic variables, whereas there would be like 7 or 8 in QCD, depending on how you count it. So it's like not really even the right dimension for the problem to compare to QCD. And 3 kinematic variables is still pretty complicated. So we've been looking around for a simpler setup, one where QCD and planar n equals 4 are even more closely related. And last fall, we found it. And that is, so I'm going to shift to a different problem, which is scattering in n equals 4, but 3 of the particles coming out are massless colored particles, gluons, and the 4th one is an operator. And just to simplify things, I'm going to call it a Higgs. This is n equals 4 super Yang, so it's not really a Higgs, but it's pretty close to how a Higgs couples to gluons. I mean, I didn't really say this in the earlier slides about Higgs production, but it's dominated by 2 gluons going through a heavy top quark loop, which couples to the Higgs. The top has a large Yukawa coupling and a strong coupling to the gluons. And so it's the easiest way to make the Higgs at the LHC. But in the limit that the Higgs mass is small compared to the top mass, which is roughly the real world, this top loop happens at very short distances, and you can integrate it out or replace all of this interaction by a direct interaction between the Higgs and the gluons through an effective operator, which is Higgs times the lowest gauge invariant operator that makes 2 gluons, which is essentially just the Lagrangian for QCD. It's the product of 2 gluon field strengths. So we're going to calculate the matrix elements for a Higgs and 3 gluons, or the analog of that, in this n equals 4 theory. These are often called form factors in the amplitude literature, but you can think of it as a scattering amplitude for a colorless particle that has a mass. And actually this mass can either be real or positive m squared or negative m squared. And you can study both cases. You might ask, why didn't we do something similar like Higgs with just 2 gluons? Well, the problem is that this has no kinematic dependence. It's just a trivially depends on the overall Mandelstamp variable. And so we need something that has functional dependence to apply a lot of these techniques. And the case with 3 gluons is just right. As we'll see in a second, it depends on 2 dimensionless ratios, which is even simpler than the 6 gluon case where there are 3 variables. So we're going to work with that one. This is what the kinematical space looks like. And so there are 3 gluons whose momentum adds up to the Higgs momentum or minus the Higgs momentum. And each of these guys are massless. So that means when we take their Lorentz square, it's 0. And using the fact that pi squared is 0, you know that the Mandelstamp invariance, which are the sums of the gluon momenta squared, are also the dot products. And if you also take and square the total sum here, you get pH squared, which is mH squared. So that's called S123, the total invariant of the 3 gluons. But if you expand out the square, you'll find that it has these dot products in it, all 3 of them. So this is what we call the Mandelstamp relation, that the sum of the 3 two-particle invariants, S12 plus S23 plus S31, is the sum of the masses in the problem, but there's only one mass, mH squared. So this is the kinematics. There are these 3 Mandelstamp variables that add up to mH squared. But it's better to scale out something and just talk about dimensionless ratios. So to do that, we'll scale out the Higgs mass squared, or S123, and we'll define these ratios U, V, and W as ratios of 2-particle invariants to the 1 3-particle invariant. Now, when we do that, you can see from this equation that U plus V plus W should be 1, if we look at this equation here. So these 3 variables, they have a symmetry relating them, but their sum is 1. So there's a triangle, a natural triangle. Inside the triangle, U, V, and W are all positive. And then this is the line U plus V equals 1 or W equals 0. So as you move across here, W switches sign. And as you move across here, U and V switch signs. So there are various kinematic regions. The one in the middle turns out to be the one relevant for a Higgs decaying to 3 gluons. And it's sort of Euclidean. Things are basically real there. But these other regions are scattering regions where you have glue to Higgs glue or Higgs glue go to glue. And in one case, the Higgs is positive mass squared and the other negative. So that's the basic kinematics. And we have various functions of U and V that we need to determine to solve this problem. Now, before I solve this problem, I want to step back a bit and take the Higgs mass to 0. So when I take the Higgs mass to 0, then the Mandelstamp constraint is the one for all massless scattering. You might know it as S plus T plus U equals 0. In that case, instead of there being 2 dimensionless parameters, there's only 1. And when you have massless particles, the only thing you can really ask that doesn't have to do with the overall energy, which you can scale out, is what was the scattering angle in the center of mass, theta. And so that one parameter must basically be the scattering angle. And if you work it out, you can also introduce a parameter x, which is the ratio of S23 over S12 with a minus sign. And if S12 is bigger than 0, so 1 and 2 are coming in, then x is 1/2 1 minus cosine theta. And that, as theta runs from 0 to pi, runs from 0 to 1. But in other channels where 2 and 3 were incoming or 1 and 3 were incoming, x would have these other values. So to cover all the channels in this case, you have the whole real line with some special points, 0, 1, and infinity. And I'm mentioning this case because it's even simpler than the 2-dimensional case. It's just a 1-dimensional problem. And we know functions that have special behavior at 0, 1, and infinity. And they're very important for this massless scattering case. And these are generalizations of the classical polylogs. So you might have seen the classical polylogs in a math course or in one-loop calculations. You may have seen the dilogarithm. And they're basically found by integrating First of all, the first one is minus log of 1 minus x, which is the integral from 0 to x dt over 1 minus t. And then from then on, you just integrate dt over t. If you do a Taylor expansion of this log and integrate it term by term, you'll find another representation of the n-fold polylogarithm that looks like this. Now, this has special behavior as x goes to 0, 1, and infinity, but it's because you can see that values of 1 and 0 are clearly special, but it's not quite general enough. So Remedi and Vermaasreman introduced this. The mathematicians knew about similar functions before. They introduced these harmonic polylogs. In this case, you integrate dt over t or dt over 1 minus t, but you can choose either one at each step. So at each step, you have two choices. This vector w here, the elements of the vector are 0 and 1. So it's like a binary code. So the number of possibilities at weight n, when that corresponds to n integrations, is the length of the binary string is n. And there are 2 to the n possibilities, 2 choices at each integration. So this is the integral definition, but you can also give a derivative definition. If you just differentiate this function here, so I should have emphasized that if the h starts with a 0, then the last integration was dt over t of a weight vector that doesn't have the 0 in it. And similarly at 1, it's dt over 1 minus t. If you differentiate it, you see that if the h starts with a 0, then you get a d log x. That is, this becomes dx over x, which is the derivative of log x. And over here, it becomes d log of 1 minus x. So you have these 2 kinds of derivatives, that every function has either a d log x or a d log 1 minus x. These functions have been proven to be very useful in the past. And in fact, one of the people I met in Mexico last year was Maria Elena Tejeda Yeomans, and she worked on the two-loop story back around the turn of the millennium. And the two-loop story, it was realized through also other work on the integrals by Smirnov, Veritin, and Tausk, that, well, the worst possible integrals at 2 loops, when everything else is massless, was this planar double box and this non-planar double box. And they could all be expressed as harmonic polylogs of the type I just described, where the maximal length of the weight vector was 4, which happens to be 2 for every loop, 2 times 2. And the argument x is just what we were discussing. Then when you go into 3 loops, Svi and I and Volodya Smirnov looked at some of the, well, this extra integral. I think Volodya had already done this one. And they also involved the same space, but now with weights up to 6. And then more recently, about 5 years ago, Johannes Henn and Bernard Misselberger computed all the non-planar integrals with this kind of topology, and they all live in this space too. So for 2 goes to 2 scattering through 3 loops, the functions that you need all have this property. They depend on one variable, x, and the derivative of any transcendental function with respect to x has a sum of 2 terms, where fx and f1 minus x are also transcendental and in the same space with one lower weight. And this is just a way of restating that they are all these harmonic polylogs. Because if you differentiate any harmonic polylog, you either get dx over x or dx over 1 minus x. And so every function in this space should have this property. So that's pretty cool that you can kind of give a unified description of all of these integrals for the massless case. And now what we want to do is the same thing for the case of 1 mass. And back at 2 loops around the turn of the millennium, German and Remedi worked out these integrals, and they were used for another process, QCD processes earlier. But 10 years ago, roughly, they computed the Higgs to 3 gluon process, the same one we're talking about at 2 loops. And soon after that, in this paper, the these integrals were used to compute the stress tensor form factor, essentially the same quantity in N equals 4 super Yang mills. And they also noticed something interesting, which was that if you look at the part of that calculation that was top weight, that was weight 4, it was the same as the N equals 4 result. This is related to something that had been noticed by Kodakov, Lapatov, and Velezhanin for some other quantities that weren't exactly scattering amplitudes. But it doesn't really hold for generic scattering amplitudes, but this one turns out to be very special. It's not completely understood why. At least at 2 loops, it seems this principle seems to hold. That if you take the most complicated part of the QCD result, it can be predicted by the N equals 4 calculation. Now, what are the functions that describe this more complicated kinematics? I characterized the the massless case by 1D HPLs, or by the derivatives being 1 over x and 1 over 1 minus x being special. Now we have functions of 2 variables, but you can characterize the whole space by this property, that there are these variables u and v, and the u derivative, by symmetry, the v derivative can be obtained. The u derivative has just 4 terms involving these denominators. And these are were called 2D HPLs by German and Remedi. There's a much broader set of things called iterated integrals or multiple polylogs that these can all be embedded in. And they generally involve these d-logs. And so this is a special case. And we generally look at all of these denominators and we call these things symbol letters. And here you see we have u and 1 minus u. This is really w and 1 minus w. And the v1 involves v. So you can see by looking at this formula that there are 6 possibilities for these d-logs or these denominators. So we say the symbol alphabet is has 6 letters in it right here. So we can use this as a definition of the function space and then try to build the function space to higher weight and impose some constraints. Now, the constraints were not very well understood for this case for a while. There were constraints for the 6 gluon amplitudes, and that's sort of why we started with that first. And those come from an operator product expansion based on this flux tube method that I described earlier. And only very recently was there an OPE for form factors. And the amplitudes in this theory have a secret life as vacuum expectation values of polygonal Wilson loops. And this picture was used, I don't have time to go through all the details, but it was used to analyze this limit where 2 gluons get parallel. And so 2 edges of this polygon, because they're these same vectors, get very close to each other. These actually can be remapped using the conformal symmetry into a situation where 2 things get very far apart. And then there's an operator product expansion that is low-lying states dominate. So that picture was used by Alday, Gaiotto, Maldacena, Sever, and Vieira. And then the integrability of the flux tubes was exploited by Basso, Sever, and Vieira, also working with Caetano and Cordova to really solve this problem in this collinear limit. And I can't really go through the details, but let me just say that it gives us all the boundary conditions we would ever want to solve the problem in the bulk. The new thing that happened this last year was work by Sever, Tumanoff, and Wilhelm, generalizing this to where you have an operator, like in a form factor. And so they needed to discuss Wilson loops, which weren't closed. The momentum of the operator means that it doesn't come back to itself here. And instead, you can kind of make it periodic with a shift. And you need some new ingredients. But now that they've worked it out, we have boundary conditions for this form factor case too. And I'm really running short on time. So I'm going to skip through this, but there are infrared divergences that happen in all of these quantities. Whenever you have external gluons, they can exchange gluons among themselves. And in this Wilson loop picture, you have the same divergences, but they actually look completely different. They look like ultraviolet divergences. But there's a close matching between these two. And we know how to remove all the infrared divergences in these quantities by dividing by a suitable function. And doing that, we get a quantity called the remainder function, which can be computed in the near collinear limit using this form factor OPE. And we can use that boundary condition data. There's a story about exactly what you want to compute when you do this amplitude bootstrap. And I'm not going to be able to go through it, but it's a form factor normalized by a certain kind of ansatz, BDS-like ansatz, you could call it. And it's related to the remainder function through the one loop answer and the cusp special quantity, the cusp anomalous dimension. And this thing has some amazing properties. It lives in a space that has a lot of extra constraints on it. So we know a lot about the branch cuts that we need, and most of those functions would have bad branch cuts. And so we throw them out. That is at weight 1, where we just have logarithms. We don't allow log of 1 minus u. That has a branch cut in an unphysical location. But log u, log v, and log w, they're all allowed. There are some technical details of what you have to impose at higher weights, which I'm not going to go through. But if we did that, we would still have we'd have a lot of functions. We would get a factor of 4 more functions for every weight. Whereas hexagon functions in the 6-gluon case, once we learned what the space was, they grow much more slowly. So we found another constraint, which applied at 2 loops, which says that the letter 1 minus u should not be next to 1 minus v, and various dihedral permutations of this. And that cut the growth rate of the space down to 3 to the weight instead of 4 to the weight. We also verified that this.
Sorry, we have 5 minutes.
Yeah, I should wrap up here. Thanks, Lorenzo. Anyway, we were able to build up this space, this space actually has dimension exactly 3 to the weight. And then we can do what I was saying earlier. We have this dimension of the space. We can find the answer in the space and uniquely fix it and check it in various ways. And then we can actually plot the results. So I'll skip most of this. So I showed you this phase space before, and it's not so easy to plot a 5 or 6 loop result everywhere in the space. But once we pick special lines, then the functions simplify and we can work them out and plot them. So they're like these 4 special lines. This one, everything is real. So I'll show you it first in this Euclidean region. And it's kind of amazing. This remainder function is forced to go to 0 here and here by certain collinear constraints. And just to normalize things, I'm going to divide by the value at the peak, which is a symmetric point in the middle of the triangle. And you can see that as you go from one loop to another, the shape of each individual coefficient hardly changes at all. In fact, 4 and 5 are basically on top of each other. 6 is a little further off, but it's almost in exactly the same place. So there's a kind of a message that there's a lot of similarity between these higher order quantities as a function of their kinematics. And we have a lot more plots, but I don't have time to go through all of them now. And some of them have to do with high energy or Reggie limits. Let me just wrap up by saying that we now have a new playground to bootstrap, which is in some sense even simpler than the ones we were doing before, these form factors. And there's rich information about different kinematic limits, and it's a 2-dimensional plane, so we can sort of see everything that's going on instead of just poking around in little special cases. And there's great synergy with this other approach, the flux tube approach or the Pentagon FFOPE approach. In fact, our perturbative information also helped them when they were constructing the form factors. So there's quite a bit of give and take here. And then this opens up a lot of future work on how you can go to finite coupling, as I mentioned before. So I'll stop here, and thanks for your attention. Happy to take any questions if there's time.
Okay, thanks a lot. Very interesting talk, Lance. Questions?
Maybe I can ask something.
Okay.
So you mentioned these Higgs gluon processes.
Yeah.
What would be the operator you put in N equals 4 for the Higgs?
Oh, well, you can just use the same operator, the field strength. It sits in a supermultiplet, okay. So you don't have to use that one. If you want to have gluons in the final state, that would be the one you would use, would just be F mu nu, F mu nu. But okay. You can rotate it into, it's like in this BPS protected operator. So if you want to make scalars, you can do something like phi dagger phi, but not the Konishi combination. There's, if you do some kind of traceless combination, I think maybe it's called the 40. I'm not as up on the, I'm not sure if it's called. Yeah. Anyway, there's a combination of phi dagger phi, which is in the same multiplet. So if you like to calculate with external scalars, you can use that instead. Okay. But there are other choices too. It's a big super multiplet. And an interesting question is, what about form factors of other operators? And at 2 loops, some of the same people, Brandhuber, Travellini, Gang Yang in particular, have been doing higher dimension operators. So if you want to go to the next order in the expansion of the Higgs mass divided by the top mass, then there's a F cubed operator that has 3, it's dimension 6. And you can supersymmetrize, well, maybe not all of them, but maybe some of the operators you can supersymmetrize and discuss. So that's interesting, but again, we need a little bit of data sometimes to get started. Once you have more data, then you can trim down, then you can figure out subspaces that the amplitudes are living in. And then you don't need the boundary data, as much of the boundary data.
We have time for another question.
Can I make a question? So,
okay.
So you were talking about these polylogs, but if you add masses to the propagators, you know that there is this elliptic function. Do you know there are some advantages in the field working on this new integral in the elliptic functions?
Yeah, there's a lot of interest in elliptic functions. And that will be part of the story too, eventually, I think. There's the elliptic functions, as you said, they show up early when you have masses. Like just for top quark production, there are elliptic polylogarithms that show up at 2 loops for glue to TT bar. You can also see them in N equals 4, but it seems that you have to go to 10 external legs before they show up. Maybe a little earlier, but for sure they show up at 2 loops and 10 points. And they're closely related to 1 loop string integrals, because strings have a world sheet instead of a world line, and that makes a torus. And that torus tells you there could be elliptic, and these elliptic polylogs show up there too, before you integrate over the shape of the torus. They depend on a torus parameter tau. So there's lots of interest in this. And one of the things to kind of understand better is how this, I characterized this derivative, and I said it was related to something called a symbol. So you have to modify or generalize those notions to handle the elliptic polylogs. But there's a lot of interest in doing that. There's also a lot of secret things that happen. There's something called a coaction principle that is understood in the polylog case, and needs to be generalized to the elliptic case to handle more realistic things. For loop G-2, that's also elliptic. That's another, the anomalous magnetic moment of the electron at for loops. That's where it first goes elliptic. So that's another motivation for understanding the elliptic stuff better. But it's starting to be understood, but I don't think it's, you know, at quite the level of the polylogs. It's much more complicated.
Thank you. Thank you.
Great
Okay,
question.
so we thank Lance for his talk, and we'll move to the next one. So,
can I share screen already? Do you see? Okay.
Okay. So we'll move to the second talk of this first part, and this is by Lucia Cordova, and she will talk about symmetric bootstrap and the space of quantum field theories.
Okay, so first of all, thank you very much for the invitation. It's a pleasure to be here. Hopefully next time we can meet in Mexico. It's a good excuse to go back home.
Sure.
So today I will tell you about this S-matrix bootstrap program and how we can use it to carve out the space of QFTs. So this is the outline of the talk. I'll give some introduction and motivation to the problem. And then, since the revival of this program is fairly recent, I'll spend a big amount of time here in reviewing the S-matrix bootstrap basics. So hopefully by the end of the talk, you will understand how this works. And then I'll review some results in two space-time dimensions. So I'll introduce this object we call the monolith, and then a very useful dual formulation we found out for this problem. And yeah, some final remarks. So please interrupt me if you have questions. I prefer that there are questions during the talk and not only at the end. Also, I have the presentation on my iPad, so if you have questions, I can even write down there. So yeah, let's make it a bit more informal. Okay, so this is a QFT conference. So I guess I don't need to convince you that QFTs are great. But perhaps I can remind you of a difference between weak and strongly coupled theories. So for weakly interacting theories, we know how to treat them. So we can compute observables by using perturbation theory. So if we want to compute some cross-section, as Lance was saying, we can start from some Lagrangian, draw Feynman diagrams up to some loop order, and obtain a good approximation to this observable. But for strongly coupled theories, this is not the case. We cannot use perturbation theory, and they are much harder to handle. So what I'll be talking about here is this non-perturbative approach, the bootstrap. It's not the only one, but it's the one I'll be talking about. So the idea of the bootstrap is to, instead of making an approximation to compute some observable, we can impose consistency conditions arising from some general physical principles. And this idea is not new at all. It has its roots in the S-matrix program of the 60s, in which they were trying to describe the strong nuclear force. This program fell a bit out of fashion after the rise of QCD, but this same bootstrap philosophy was applied very successfully in conformal field theories in 2 dimensions in the 70s and 80s. And one of the reasons of this success is that they were able to find exact solutions to these consistency equations. So do you still hear me? Let me know if something was wrong. Thanks.
Yes.
Yeah, so they found exact solutions for two-dimensional conformal field theories, but for more complicated cases like higher dimensions, it's much harder to find exact solutions. So this program fell a bit dormant until around 2008. A new idea came in, and this is instead of finding some exact solution, one can derive bounds and rule out possible candidate solutions. So if you want, you can think of it as a black box where you input some data characterizing your candidate solution, and it spits out a no or a maybe. So a no would be, no, this data is not consistent with the principles you're imposing. And a maybe is, yes, it is consistent, but maybe you're not imposing everything you need. So this is a very powerful idea. And to give an example of a type of bounds you can get, there is this very famous plot by these authors. They were doing some numerical analysis using this bootstrap philosophy, and they were studying the three-dimensional critical Ising model. So here we have some critical exponents. And what they did here is this exclusion plot where they say everything except this tiny island is excluded by this bootstrap idea of imposing consistency conditions. So it's very impressive, and actually I think still up to now, this is the most precise prediction for these critical exponents. So, okay, I'm not going to talk about conformal bootstrap, but the idea I want you to get with this slide is that the bootstrap philosophy is very powerful. And even if we cannot find exact solutions to these consistency conditions, we can derive bounds and still get very interesting results. Any question about the general philosophy? Okay. So the main question motivating the work I'll be describing is, what is a space of massive quantum field theories? So in a very abstract picture that I will make more precise later, we could imagine having some region where consistent QFTs live. So this is in some parameter space. And we want to know what this region is. What are these theories at the boundary? Are there special points leading to some interesting theories? And as you might guess, the idea is to explore this space using the bootstrap philosophy and S matrices. Okay, so this is a motivation. If there are no questions, I'll go to describe the S matrix bootstrap. So, of course, sorry, no, I have to say this first. The general idea of the S matrix bootstrap is to compute a non-perturbative S matrix from these three general principles. So first we have unitarity, and this is just telling us that probabilities should sum up to 1, since we know a probability for certain scattering process to occur is related to some S matrix element. Then we have crossing symmetry. That's my cat, sorry. Which tells us that different scattering processes can be related if you send incoming particles to outgoing ones. So if you switch in and out particles, those processes can be related. So here, for instance, we have some 2-to-2 scattering, and this should be related to the one where I take one of the outgoing ones to an incoming state and A2 to outgoing. So that's crossing symmetry. And finally, we have analyticity. And this tells us about the possible singularities in the complex plane of these S-matrix elements as a function of their kinematic invariance, for instance, the center of mass energy. And these functions should be analytic, except for possible singularities that you can determine by on-shell processes. So for instance, bound states would correspond to poles in a complex plane. I'll give precise equations for a simple S-matrix element in the next slide. Okay, so as I was saying in the introduction, this idea is not new and was used already in the 60s. But the revival of this program came a few years ago, and they were very much inspired by the conformal bootstrap. And there again, instead of finding a unique S-matrix, they tried to constrain the space of QFTs by putting bounds in the possible S-matrices. So let me review the simplest setup. Okay, are there any questions? So let me review how this works precisely in the, yeah?
Can I have one question about the?
Yes.
What do you mean, a bit more precise, by the space of quantum field theories?
Yeah, so hopefully it'll be super clear when the talk ends. But basically, I'll be looking at the space of S-matrix elements that obey these conditions. And of course, in general, this is something really, really hard. So if I want to do this for any S-matrix in any dimension, it's something really hard. So one starts with simpler scenarios. So, sorry, is a question more or less answered?
Yeah, thank you.
Okay. So the simplification we will do in this talk is that we will work in two space-time dimensions. So there's just time and space. And we won't look at the full S-matrix, but just the 2-to-2 S-matrix elements. So we will be looking at processes of this type. We have all the in and outgoing particles with the same mass. And we have 2 in and 2 out with their momentum. So now let's see what this S-matrix element should obey. First, we have Lorentz invariance. So this tells us that it should be a function of the 3 Mandelstamp invariants you can write. Lance already introduced them. And in 2 space-time dimensions for this 2-to-2 scattering, you can see that the set of incoming momenta is the same as the outgoing one. So you basically can set U to be 0. And you have only S and T. And they should obey this equation here. So since they are related, S and T, by this equation, you have only one independent variable, S, which is the center of mass energy. So that's what we know from Lorentz invariance. Then how do we impose unitarity? This is the condition that this S-matrix element, which I will call S-matrix at some point, but just remember, I'm always thinking about this 2-to-2 scattering. This S-matrix element, its absolute value is bounded by 1 for physical values of the center of mass energy, that is for S bigger than 4m squared. And this inequality comes from the unitarity of the full S-matrix. What is equal to 1 is the probability of 2-to-2 and 2-to-n all sum up this is equal to 1. So if we're not looking into all these processes, then we just impose this inequality. That's unitarity. And then crossing relates the S and T, well, the S matrix of S and T. And you can see it simply from how time flows in this process. So you can look at this picture as time going in this direction. So these are your incoming particles, but you could also flip them. So you would see the processes in this direction, and these are the incoming ones. So you see we get T instead of S, but T is for m squared minus S. So crossing symmetry gives you this relation. And now let's look into the analyticity properties. So in this complex Mandelstamp S plane, the type of singularities we can have are here. So first, when you have some bound states, so when you can draw some process like this, you would get a pole at the position mb squared, where mb is the mass of this bound state. And then by crossing, we get a similar pole here. Then for higher particle states, 2 or 3, we would get cuts. So we have a cut starting at 4m squared. That is when you can start drawing processes of this type. You could have higher thresholds here, so cuts starting later. And you have a similar cut starting at 0 from crossing. And the physical values of S would be here right above the right-hand cut. Yeah, so otherwise they're analytic, there are no other singularities. And of course, these poles, for instance, would depend on your theory. You can have a theory without bound states and there you don't have any poles. Or you can have many bound states and you will have many poles. Any questions so far? Okay, so now that we know all these properties this 2-to-2s matrix element should have, let's write an ansatz for it. And we will use the so-called dispersion relation. And this is very simple to derive. So basically you use Cauchy's theorem. So you start at some point S here with some contour around it. You can write this equation, but then you can also blow up this contour and pick up the singularities in the complex plane. So you would have these poles at S equals mb squared, or T, which is 4m squared minus S equals mb squared here. And the residue at this pole is what defines the non-perturbative coupling. So this G squared is the non-perturbative cubic coupling here. Then we also pick the discontinuities across these cuts, and they're parameterized by this function rho. And okay, we have the value at infinity, this S infinity. So with this dispersion relation, we have taken into account all the analytic properties that we know, and also crossing symmetry. So it's a nice ansatz for the S matrix. So now let's go into the bootstrap. And the recipe, if you want, is the following. You first choose some spectrum of the theory. You say, I'm interested in a type of theory where I have some state of mass m, which I'm scattering, maybe some bound states, maybe not. So you choose the spectrum first. Then you make an ansatz for this 2-to-2 S matrix element. You can use the dispersion relation we derived here. And finally, you would like to maximize some function now of this function S of S, the S matrix. Usually one needs to do this numerically, so one would discretize this density rho, but okay, I won't go into the details of the numerics. And you also need to impose unitarity for some, well, for all physical values of S. And an example of a type of bound you can get following this recipe, which is what we call the primal problem now, is to get a bound for the maximum, for the cubic coupling in a theory where you have only one bound state. So again, we choose our spectrum. We have our state of mass m, which we are scattering, and one bound state. And we want to put a bound on this cubic coupling between them. So as I told you, this cubic coupling is defined as the residue at the bound state mass. So we would be maximizing this functional, just g squared. And the physical intuition for having a bound of this type is that you're fixing the spectrum, remember. And as you increase the coupling, you're also increasing the binding energy between these states. So you would expect that at some point you would create more bound states, and that would be in contradiction to the spectrum you're fixing. So this is a physical intuition as to why there should be a bound for these couplings. But let's see what the result of this simple problem is. And you can see it in this plot here. So this blue line is a maximum g squared you can have for different bound state masses. So you fix your bound state mass and m, you maximize, you get 1 point, and you do it for various MBs, and you get this. So, okay, it has this symmetry because of crossing symmetry. You see that it goes to 0 around threshold. It has this divergence at square root of 2 that you can understand from the screening of the S and T channel poles when MB squared equals 2. And what this plot tells us is that theories with this spectrum and a cubic coupling, the cubic coupling for this theory should be below this curve here. So if someone tells you, oh, I have a theory with a spectrum and a cubic coupling here, you can say, no, this is not compatible with unitarity, crossing, etc. So they should be inside. But a natural question to ask is, is there a theory, a particular theory corresponding to this boundary value? What is the S matrix there? So you can actually get the S matrix from this maximization procedure. You don't only get whatever you're maximizing, but you get the full S matrix since you have an ansatz for it. And you can check that the function maximizing this G is this one here, where theta is a rapidity variable related to the center of mass energy S. Here, it's very used in interability. So it's a very simple function, and you can see that it reproduces this bound. Actually, you can get this bound analytically, but okay. In general, you can't. So this S matrix here corresponds to the S matrix in Sine-Gordon theory for breather bound states. And this is a well-known theory that is iterable. So since some iterable solutions will come in, I will make an iterability parenthesis. So iterable theories are typically two-dimensional. They have an infinite set of conserved charges. And this tells us, among other things, that all scattering processes can be related to a sequence of 2-to-2 scattering. So for instance, for this 3-to-3 scattering, we have that they should be computed by the sequence of 3 2-to-2 scattering, but we could also do it in a different order. And this condition here of the different orders is what is known as the Yang-Baxter equation. And by imposing this condition, one can get various different exact S matrices. So it's one big advantage of working in 2 dimensions. So one is that it's just simpler, there are less variables. And the other one is that you can make contact with known exact solutions. Okay, so this is the review of one of the simplest examples of a bound we can get with this S matrix bootstrap. Are there any questions?
What about the massless case?
Massless case. So you can also treat it in this formalism. There's been some work in that as well. The main difference is that here you would have these cuts colliding. So you're making an ansatz for a function in the upper half plane, but you can still say things about those. I will be focusing in the massive one though.
Okay, thank you.
And just for comparison, Lucia,
Mm-hmm.
like if we have like a real hadron coupling, like rho to 2 pions, where are they in this plane that you have?
Yeah, so I don't know if one can translate it to this 2-dimensional case. If you can, they should be below, of course.
In the row is above the pi threshold, so it's not a good analog for this case, I guess, right?
The row is it's a resonance, right? It's true. So yeah, it's there's this distinction between bound states and resonances. You would see the resonances as poles, but in the second sheet. So if you go to, yeah, we call this sheet where you evaluate unitarity, the physical sheet. But if you go through these cuts, then there are many other sheets, and the resonances would be poles in those other sheets.
Okay, thank you.
Can I ask a question too?
Yeah.
So if you look at your plot on the allowed versus unallowed, and you go up near MB over M near 2, that's the part that you were explaining intuitively, I think, that, you know, as you increase the coupling, the bound state comes down, and so kind of moves you along the left. But do you have an intuitive understanding of the part of the plot near where MB over M is near 0, where the bound state is very deep, or why the coupling is coming down there?
Yeah, so actually I shouldn't be presenting this plot below 1.
Okay.
Yeah, you can see if you just flip the sign of the solution, you get this other one, and it matches all the way to 1. But to be completely correct, you cannot, in order to write these analytic properties and nothing else, I'm also saying that M is the lowest mass in the theory.
Okay.
Because otherwise you can have anomalous thresholds, etc.
Okay. So we shouldn't really look at it below 1. And then the square root of
Yes.
2 peak again. Could you say that one more time? I kind of missed that.
Yes, so it's basically because these two terms cancel. So if you see t is form squared minus
Okay.
s, so the residue has the other sign. And when mb squared is 2, then they just cancel and you cannot get a bound.
Great, thanks a lot.
Yeah, more questions? Okay, so now let me pass to some other results in 2 dimensions. We will consider a generalization, a simple generalization of what we did before. We're still in 2 space-time dimensions, scattering particles with the same mass. But now we have some global symmetry. We choose this group to be ON. And each of these scattered particles transforms in the vector representation of ON. So they carry some flavor index that runs from 1 to n. And now my S matrix element will have these indices ij, kl. But again, it only depends on one Mandelstamp invariant. So how do we take care of these ON indices? We basically write the allowed tensor structures in this group. So we have these Kronecker deltas. So the trace, identity, and permutation, what the flavors can do, how they contract. And this leads us to 3 different functions. In these bases, we call them sigma 1, sigma 2, and sigma 3. But of course, we can also project into the different irreducible representations. So we have 3 irreps here. It can be singlet, antisymmetric, or symmetric. So again, we have 3 functions S of A, where this A labels the representation, and these are the projectors, or just linear combinations of these Kronecker deltas. So now instead of 1 function, we have 3. And to impose unitarity, it is very simple in this representation basis. In each representation, we have the same condition that the S matrix is bounded by 1 for physical values of S. And then crossing, again, if you want to see this process in this way and say it's the same as looking at it in this way, you see that sigma 1 should be related to sigma 3 at T and sigma 2 to itself. So we have this condition here in this basis. And in the representation one is a bit more complicated since it mixes the different representations. The matrix CAB here is, these are just numbers with the parameter n of the ON group entering there. So we have 3 functions bounded by 1 on the physical line, and they're coupled through crossing in this way. So it's a simple generalization, but we will see it's actually very rich. And again, to do the bootstrap, we fix our spectrum. Now we have more choices. We can put bound states in different channels, in the different representations. And we would maximize some function all of these 3 functions S of A. Okay. So now let's, if there are no questions, let me go to the results. Let us focus in a case without bound states. So the analytic structure of this S of A doesn't have any pole, just the possible cuts. And the question now is, what is the space of allowed functions or S matrix elements SA of S? So one thing we know already about this space is that it's infinite dimensional because we have this continuous parameter S. And the idea is to explore it again by maximizing some functional. We will choose this functional here, which is a combination of these S matrices at a given point S star with some coefficients NA. And one thing we can do is to plot subsections of this infinite space. So we like 3 dimensions because we can see things. So we did 3D subsections of this space. By the way, this type of functional, you can think of it as some effective quartic coupling. Okay, so let me show you one 3D subsection, not this one. Yeah, here. So this is something we found numerically. We actually 3D printed it, but okay, this is what I can do over Zoom. And you see there are some very nice edges. You can see some vertices. Okay, so this is what we call the monolith. And now let me show you, whoops, okay, I didn't want to do that. Yeah, let me explain some of the features of this monolith. So it's something we published in this paper here. And this is just rotating what you saw. We found this by, of course, we fixed n to be some number. We did it for various n's and we get something similar, nothing special about 7. And we get this by running this bootstrap problem with 200,000 different NAs. So each of these crosses here is a point that we run numerically, and we're fixing S star to be 3m squared. Again, you can look at different S stars and the physics does not change. So now what do we know about the S matrices here at the boundary? What are these vertices? So the first thing we can say is that we get interval theories at special points here. So the first one, these are the axes. So it's in these sigma 1, sigma 2, sigma 3 bases. These are the allowed values that these 3 functions can have at that particular energy. Okay, so the most pointy point in the monolith, this vertex corresponds to free theory, which is just all S matrices equal to 1, and it's a vertex of the monolith. Another interesting point is here. So it's not super obvious here, but there is an edge that ends up there. So it's actually a vertex as well. Perhaps I can, yeah. So you see there is this line. And you can feel it in the 3D print. So it's this point here. And that's the nonlinear sigma model, which is a known model whose S matrix was found or bootstrapped in this interval bootstrap sense by Zamolodchikov and Samolodchikov in the 70s. And it's a simple ratio of gamma functions with this rapidity variable, and n comes in some particular way. Another interesting point we found is here. So it looks like a vertex, but actually these edges here flatten out as you get closer and closer. So we call it pre-vertex. It seems to be special, but it's not an actual vertex. And this is also an interval solution. So it obeys this Yang-Baxter equation I mentioned at the beginning. And the exact S matrix is given by an infinite product of these gamma functions, and was proposed in 79 by Ortaxu et al. Just as a solution to Yang-Baxter, but we don't know if there is a model with this S matrix. So it's an interval S matrix, but we don't know if there's a physical model behind. but you see it has a special space, a special point in this space. And finally, we found some other interesting point here, which is not integrable, but it's just some constant solution, where in the singlet channel, it's just 1, in the antisymmetric -1, and in the symmetric, you have this ratio depending on n, which is less than 1. So yeah, it's a funny S matrix with some particle production in one channel. Okay, so yeah, we also have some exact solutions here, which are not integrable, but again, we don't know if there is some physical theory behind. And in general, we know pretty well how these S matrices look in the boundary and how to interpolate between them. There's this very nice game of how all these poles and zeros in the complex plane and all the sheets move and collide so that you can go from something which is a constant to something with infinite poles and zeros. It's a nice story, but I never have time to talk about it. Let me go into other 2 properties we found of this monolith. And a very mysterious one is that there is some emergent periodicity at the boundary of it. So here I'm plotting a 2D subsection instead of a 3D one. This is sigma 1 and sigma 2 at 2m squared at the crossing symmetric point. But still you see the same known solutions at the boundary. And what we found is that for this 2D subsection, they are exactly periodic. So they obey this equation here for some period tau. And this period changes as you move along the curve. So if you start here in free theory, it would go to infinity because okay, it's just a constant. But you see that it starts decreasing up to some minimum that you have here for this special periodic Yang-Baxter point. Then it blows up again in the nonlinear sigma model, which is also not periodic, so it's fine. It goes down all the way to the constant, all the way to 0 in the constant solution and blows up again. But in the middle, all these things are periodic. And physically, this sounds very strange because this would say that the S matrix is periodic in some parametrization of the energy. So theta is like log S. So it doesn't look as mysterious if you think about just maximizing some functions that are phases at the boundary. But still, we haven't been able to prove why this is a solution to this optimization problem. And they might also have some physical meaning. So, okay, this is mysterious. And another thing we saw is that generically we have unitarity saturation. That is that this 2 to 2 S matrix element is actually 1 and not just less or equal to 1. So it saturates unitarity for 2 to 2, which means there is no particle production. And this really only makes sense for integrable theories. So for the non-integrable points, the bounds, the physical bounds should go down once we include more and more particles in our bootstrap. But we actually understood why, from the optimization point of view, we get this generically. So, okay, the last thing I will tell you about is this dual formulation that we found. And it's actually very simple to derive, so I'll do it here in this slide. Remember, we're considering functionals of this type, where we evaluate the S matrix at a point with some coefficient, NA. So again, using Cauchy's theorem, we can write it like this. The only thing we need to impose is that Ka has a pole at this point here with a residue Na. So this is just Cauchy's theorem. But now we can again blow up the contour and write this integral like this. So if we assume that k decays fastly enough at infinity, we just get rid of these arches. So we have the contribution around these two cuts. And the discontinuities can be related to the imaginary part. So we get the imaginary part of k times s. And also, if we impose some crossing symmetry, some type of anti-crossing symmetry for these dual functions k, since this matrix square to 1, because if you cross twice, you get the same thing, you can actually write it just in terms of this part here. So you get twice this part here, because you would need both left and right hand cuts. So far, so good. Now, the only thing I'm going to do is to say that the imaginary part should be less or equal than the absolute value. And since I'm evaluating this integral in the physical line, we can use unitarity and arrive at an expression that depends only on this dual function k. So this is what we call the dual functional. And it has many advantages. So it gives us a bound on the maximum of this primal function that we were discussing. This maximum should be less or equal than the minimum of this dual functional. And it has basically two advantages. The first one is that it gives rigorous bounds. So before, what we were doing was to construct explicit S matrices that satisfy the properties we wanted. So we were exploring this space from the inside, and going out. And as we have better and better ansatz for S, we should converge to this optimal bound in black. But these are not rigorous bounds, because we don't have the most general ansatz in general for S. And with this dual problem, we can get rigorous bounds. So it's more similar to the conformal bootstrap technique. And there we explore the space from outside in. So as we have larger ansatz for k, we get closer to this optimal bound as well. And we rule out whatever is outside rigorously. Also, numerically, it's sometimes easier in general, it's easier to get bounds with this, because you don't need to impose unitarity as you have to impose here. And it also explains the generic unitarity saturation that we saw. And this is because for this particular type of optimization problem, we know that this is actually an equal sign. So there's something called duality gap, and this is a convex problem. So we have an equal sign. And if you go back to the derivation here, to have an equal sign here, you need either SA to be saturating unitarity, or KA to be 0. So generically, K is not 0, and we have SA equal to 1, except, of course, this constant solution that I mentioned, where the symmetric channel has some particle production, and there Ka is 0, as it should. So it explains something that was observed in many bootstrap problems, and this generic unitarity saturation in terms of this optimization problem and the dual formalism. Okay, so I'll summarize quickly. I introduced the S-matrix bootstrap program. I showed how it works in simple cases, and we explored the space of 2D quantum field theories with it. we found many interesting theories at the boundary. There is some connection to interoperability. And also I talked about this dual formulation that, as I explained, is important. And well, since this program was revived, there's been a lot of momentum. So there's been a lot of work on it, and people have studied various different cases, also in higher dimensions. But some questions I'm interested in is, what are these S matrices at the boundary that are periodic? Is this periodicity something interesting physically? Then a very, well, this is very hard, but something we should do as a community is think about this problem for higher point amplitudes. This is something very hard, especially for the analytic properties that are not well known. Then also this dual formalism for other problems, especially in higher dimensions. This is actually something that's being worked out by two of my collaborators that will publish soon. And yeah, I don't have time to talk about this, but there is a very nice connection to the conformal bootstrap through holography. So we can study these quantum field theories in ADS. So we put them in some ADS box, and we can take the flat space limit. And we know by holography that this induces some conformal field theory at the boundary, and we can study this problem using the conformal bootstrap. And there is a very nice connection between, say, the extremal functionals studied in the conformal bootstrap and these dual S matrices that we're seeing here. So this is something I'm exploring as well. And yeah, it's a nice, rich new program. You can look at all the papers with S matrix bootstrap on it. And I'll end there. Thank you very much.
Okay, thank you, Lucia, for your very nice and interesting talk. We have time for a few questions. Go ahead. Lance?
Oh, I didn't raise my hand, but I do have a question. Oh. You want me to? Okay, you said, Lucia, you said, I thought you said that you pointed to part of the surface of the monolith and you said that was a non-integrable theory. But then I thought that, maybe I misunderstood, but I thought the surface of the monolith was unitarity saturation. And I thought unitarity saturation was one of the ways of knowing that you had something integrable. So yeah. Can you explain that?
Mm-hmm. So there are only 3 points that correspond to integrable theories in the monolith, which are free theory, the nonlinear sigma model, and periodic Yang-Baxter. These 3 points obey the Yang-Baxter equation, as they should, and are the only ones that obey that equation. On the other hand, it is true that we find some unitarity saturation everywhere. This would tell us that if we include more amplitudes in our problem, this bound should go down whenever you're not in these integrable theories. So it's true.
So you know they're not integrable because they don't obey Yang-Baxter, not from the unitarity saturation.
Right. Okay. So in general, in these bootstrap problems, you saturate. So you're maximizing some functional, and it is natural that to maximize it, you maximize the value at the boundary. So yeah, the computer doesn't know about interoperability or that there should be particle production in general, so it just maximizes. And we now know from this dual perspective that it's just part of the optimization. But I agree they shouldn't be physical because they saturate unitarity and are not integrable. However, something we did in the previous paper about this is that even if you impose some particle production by hand, the S matrices that you get are very similar. So their analytic structure, the resonances that appear are, they maybe move a bit, but you get basically the same thing. So even if they are not physical, I would expect them to have some relevance.
Okay, thanks.
Zvi?
Yeah, hi. That was very nice. Thanks. Can you comment on on the higher point case? If are there any papers or because I hear I hear people always say to look at the higher point case, but has anyone done anything about it?
I don't think there are papers about it. I know people are working on it since a long time, but it's just very, very hard. So I think, yeah, I can give names.
So there's no literature. No literature. Okay.
In this context of
in the context
bootstrap,
of
no.
higher point. Okay.
Not that I know of. No.
Okay, Brian?
Okay, thanks, Lucia, for this nice talk. I just have a general question. I wonder if there is a implementation of this bootstrap program to gravity amplitudes, and if there is, are the people using all this power of the double copy or something like that in the program?
So I think the first papers about it came out a few weeks ago. It's somehow cheating because you're using supergravity and you're actually looking at a scalar amplitude that, okay, it's related to the graviton by supersymmetry. Okay, it's not my work, so I'll just say what I remember. They're working in 10 dimensions and looking at supergravity. So what they're doing there is to impose some of the weak, the low energy behavior, and then the rest that we discussed here, and getting some bounds as well in alpha or something like this. So yeah, there's been some very recent progress that I am not an expert, but there people are interested. Yes.
Okay, okay.
Okay, I think there are no more questions, so we thank again Lucia, and we close this session, and we come back at 3 p.m. for Zvi talk. Okay, have a nice
Perfect.
day.
Share
Yeah,
your screen,
right.
your presentation.
Right.
So let me just make a short presentation. So for the people who are not really involved in the field, and they're just only new students, Professor Bern, he's one of the, with of course Lance Dixon, one of the top people in the world who work in amplitudes, gravity, and the applications of quantum field theory and how to compute observables with the highest precision ever computed in the world. And it's been an honor for me and also to meet them last year. And now again, listening to these very interesting talks. And I let you with Professor Bern and with his talk of amplitudes and gravity. Thank you.
Well, thanks a lot for the very kind introduction. So I'm going to give an overview of a few topics in amplitudes and gravity. So I'm going to talk about perturbative gravity and then explain some of the issues, the difficulties with perturbative gravity, and then we'll talk about the antidotes to the problems, unitarity method, this double copy and color kinematics duality that we use. And then I'll just give a quick overview of of a few topics that where we've applied these ideas. And that'll be something we call the web of theories, which I won't say too much about, but I think that's something very interesting. The non-normalizability properties of supergravity, gravitational wave physics, and then a few comments. And I think many more good things are coming in the direction of understanding gravity weak coupling. So what are the problems? Well, the fundamental problem is actually pretty simple. It's things get very messy very quickly if you don't have good formalism. And the basic way that you could say the traditional way of thinking about this problem would be you start with the action, the Einstein action, and then you do a perturbative construction around some background metric. We like flat space, but you can do this around any background that you like, plus some fluctuations. The fluctuations are the gravitational fields, the graviton. And this, the Ricci scalar here is highly nonlinear. So if you were to plug this in and series expand, you'd get many, many different types of interactions, an infinite number of interactions. And as we'll see in just a minute, they get very complicated. And if you compare this to gauge theory Lagrangian, on which QCD is based, then you find in comparison that it's much simpler. There's a 3-point interaction, a 4-point interaction, and that's it. And the basic conclusion from this is that you think that gravity is much, much more complicated than gauge theory, even though they have some kind of formal similarity with general coordinate invariance and gauge symmetry. But in detail, they look pretty different. And in fact, we can quantify what the word pretty different means. And that's a comparison of the interaction vertices. So this would be straight out of the Lagrangian. You'll find, following the Feynman rule construction, you'd find the 3-vertex of gauge theory that looks like this. It's a little bit complicated, but not terrible. And then you compare that to the 3 graviton vertex, if you really care. This is in the Donder gauge. And what you find is something quite a bit more complicated. In fact, the notation hides some of the complexity. P6 means there's 6 terms. There's a permutation sum that you have to do. P3, 3 terms. The sim means you have to symmetrize the indices. There's mu and nu. The graviton is a symmetric tensor. And what you find is about 100 terms here. And they don't seem to be very enlightening exactly what these terms are. Basically, what you conclude is it's very complicated. And maybe you can push through calculations on a computer, but there's no insight into the structure. There's no relationship of the 3 graviton vertex to the 3 gluon vertex. And you can very quickly do some counting. Once you have 100 terms in a vertex, and then you count the number of terms in the propagator, you can come up with gigantic numbers just from the fact that there's many vertices and many propagators. You can get to gigantic numbers of terms, far beyond what a computer could do. So if you try to do these calculations, 3 loops, 4 loops, high loop orders, it's basically impossible. There's no way you could deal with it. I should add, there's many ways of counting it, and you could say, maybe I didn't take into account some cleanliness from field redefinitions, but it doesn't matter. I mean, basically you hit a brick wall. It turns out, let's say 5 loops, you can very quickly encounter even a single integral that's completely hopeless, just in the way it explodes. So anything at very high loop orders in gravity, it just seemed utterly hopeless. In fact, there are really no calculations beyond the simplest ones at 2 loops in gravity theories. And the various questions at high loop orders, it seemed destined for the dustbin of undecidable questions. You can make arguments. But in fact, we can deal with these types of problems. Now we have the antidote for the complexity. And one of the antidotes was what we called a generalized unitarity. And this is the idea we should be thinking about things in terms of on-shell and systematically using ideas that were developed in the 1960s about unitarity cuts. Except you could say the advances that we now understand a lot about the functions we're trying to build because we understand Feynman rules, and you can generate a systematic formalism for calculating in not only arbitrary numbers of loops, but arbitrary numbers of legs and arbitrary numbers of particles. And then there's other concepts that are related. We call them generalized cuts, where you start cutting in different channels and assembling answers. And I should mention this basic idea. This was used in what we call the NLO revolution in QCD collider physics. And we're going to talk about applying it to other problems, especially the gravitational wave problem, also the non-renormalizability problem. And one of the key points is that in these unitarity cuts, we use Einstein's relation on the intermediate steps. So what happens is the building blocks are gauge invariant. So it's a formalism where you're building gauge invariant quantities from other gauge invariant quantities. You're not going off shell. You're not trying to use quantities that are gauge dependent. For example, this vertex is off shell. K squared is not equal to 0. There's no physical state condition on this vertex. And that, in fact, is exactly why it's so complicated. If you use Einstein's relation, if we use that on-shell E square minus K square is equal to 0, this would be, let's say, a massless particle like a gluon or a graviton, then what happens is there's a fantastic simplification in the case of gravity. For the case of Yang-Mills, there's a little simplification, but it's nothing like the spectacular cleanup that you find in gravity. And in fact, what you notice is that the same object, there's the same Yang-Mills vertex. It appears twice, 2 copies in gravity. Okay, and that in fact is a crucial fact. That's the tip of an iceberg, because you might say, well, look, it's only a 3 vertex. What are you going to do with this thing? It's on shell. But the idea is that from here, given the new formalisms, the on-shell way of thinking about things, we can build, in fact, the entire theory just starting from this simple vertex. So already you're in a good direction. And in fact, a lot of the concepts were understood back in 1985 you could say the simple relations between gravity and gauge theory. So on the previous slide, this slide is, you could say, the first example at the 3-point level, we see a nice relationship that the Einstein gravity is the square or 2 copies of the gauge theory. And in fact, this idea holds much more generally. For any tree amplitude, we can find such relations between gravity, gauge theory. So this would be the Kawhi-Lewallen-Nantai string theory relations. But if we go to the low energy limit of a string, we're talking field theory. That's where these relations are written. So you could say now, if you're interested in a tree level gravity amplitude, the way you do it is you calculate the simpler gauge theory. And gauge theory, there's many, many computations because of collider physics. So you just compute on the gauge theory side, and then you just have to multiply certain pieces, add them together, and through these Kawhi-Lewallen-Nantai relations, we get gravity. So that you could say is the new way to calculate. You recycle things. And in fact, this generalizes for any number of legs. We wrote down an explicit formula many years ago for arbitrary numbers of legs. So it's something very general, and And it also works not just for, let's say, pure Einstein gravity, but it works much more generally. Okay, and one thing that I actually still marvel at, you know, we knew this back in 1985, and now you think, you know, you'd think that by now we might actually understand why this is happening, let's say from a Lagrangian point of view. So you can start with the Einstein-Hilbert action and you can ask, is this true? And sure enough, you can grind this out. We calculate the left-hand side starting from Feynman rules. We calculate the right-hand side. We compare. We declare. If you do that, you'll find it's true. But that doesn't enlighten you, right? Like the underlying principle of why, you know, how this can be true. Well, I would say more work on that needs to be done, and more needs to be understood for sure, even after so many years. And another way of looking at this problem has to do with the duality between color and kinematics. So it turns out that the secret of understanding gravity theories in a relatively simple way, it comes from not from looking at gravity theories, it comes from looking at gauge theory. And the nice example would be a 4-point amplitude. So we can think about a 4-point amplitude in gauge theory. Now, in gauge theory, there are two concepts. There's the color, and there is the kinematics, like the vertices have some kinematics, momenta in the vertices. Now, the color factors, they certainly look quite different from the kinematic factors, but and in fact, what they do for a living is they satisfy the Jacobi identity. That's what color factors do. And the reason why it does that is because it's based on a Lie algebra, and Jacobi identity is very basic to consistent algebras. You can do a little homework assignment. You can go home and give it a try. You take out the Feynman rules and you write down the Feynman diagrams. And then for the 4-vertex, what you do is use this fancy identity. 1 is equal to S over S, where S would be one of the Mandelstamp invariants that you heard about in other talks. This diagram has a 1 over S propagator. That's the Feynman diagram. And okay, this one's missing it, so you put it back, multiply by S over S. And then if you see the same color factor in here that you find in, let's say, the first diagram here, you just move the piece in. Or if you find a color factor that looks like the second diagram, you just move it in. So in that way, what you do is you write the 4-point amplitude, this tree-level amplitude, as a kinematic numerator. N is whatever you get from these vertices, the kinematic part. C is the color factor, whatever you get from multiplying together these color matrices. And then 1 over S, that's your Feynman propagator. And we have S, T, and U channels. And you can go home and calculate this, and you will discover that as long as these legs are on shell, you have to use the physical state conditions of the external legs, k² equals 0, and that the polarizations are transverse. You will discover that the kinematic numerator satisfies the same Jacobi identity that the color factors satisfy. Now, of course, this is, you could say, very nice, but it's some kind of curiosity. Okay, I mean, what of it? Well, first thing is it's actually general. This point holds in general that you can make it look at arbitrary number of legs. Let's say if you're looking at 5 points, for argument's sake. Then at 5 points, we can find ourselves 3 diagrams, find a color relation, some relation like C1 plus C2 plus C3 equals 0. And then the claim is that there is a way of arranging the corresponding kinematic numerators such that they satisfy the same identity, the same Jacobi identity. For every Jacobi identity of color, there's a corresponding one of kinematics. The constraint is that you better get the right tree amplitude. Right? So that tells you what's allowed here. And the claim is that you can find such a relation. If you try this at home with Feynman diagrams, then it's not going to work. You have to force it into this relationship. You can start with Feynman diagrams, but then you have to rearrange all the pieces in just the right way so that this is true. And in fact, there's been by now there's many proofs of this. So at tree level, this is a proven statement that you can do this. And you'd say, okay, that's very nice. At least it's general. But what of it? The what of it is right here. Let's suppose I could do that. Let's suppose I've done that. Then there's a simple rule. If I have a gauge theory amplitude and I want the gravity amplitude, then what I do is I take the color factor, I replace it with a kinematic numerator. So the color factor becomes another kinematic numerator. So the gravity amplitude is closely related to the gauge theory amplitude. Now, this is something very profound because it tells us, you could say in a bottom-up kind of way, where we're just studying Einstein gravity, we're just studying gauge theory, and we notice that not only is there a vague similarity between these two theories, that there's some kind of gauge symmetry in the two theories, but in detail, the details, like how the diagrams are built, what are the building blocks, they are identical. You find the same, exactly the same numerators, the same kinematic numerators in these diagrams. This sum is a sum over diagrams. So we're summing all the diagrams, color factors, kinematic numerator, Feynman propagators. Okay, and the two theories belong together clearly. So there's something very profound about that. It definitely cries out for a unified description of gravity and gauge theory. Presumably, it's along the lines of string theory that you think must exist. Of course, this doesn't prove anything. It's just nice to see it. Okay, and these same ideas, I could add, they are conjectured to hold at loop level. In general, making it work for a general problem of loop level is not so simple, but certainly we've gone very far with that this idea to do loop level calculations. Now, one of the kind of amusing side benefits of this is what we call the web of theories. So you can pick, in this chart, it's a collection of theories. There's a collection of theories, whatever your favorite theory is, supergravities, there's a bosonic string, heterotic string, et cetera. There's a Dirac-Born-Infeld theory. And what these lines represent is if they share in the double copy, this way of thinking, we call it the double copy, that we take there's two theories, and you combine them according to the prescription, you get a new theory. For example, we take two copies of gauge theory, and then we get a gravity theory. So each one of these items in here would be one of the double copies, and if they share there's a common theory that's shared, like a building block theory, then we connect them. So this points out to various relationships between theories that you think would have nothing in common. And this is, I think, something also very profound. It's as if though you could say that in the realm of physical theories or theories that make sense, nature likes to repeat. There's a repetition. The same thing happens over and over. Just like in the case of say gauge theory, and we go to gravity, we see the same object appearing once, and then the same object appears in another theory. Now, there's, I guess, we're going to have a talk, I think it's probably later today, if I'm not mistaken. Andres Luna is going to talk about the classical double copy. So if you notice, I've been talking about the case of perturbation theory, scattering amplitudes, and you say, okay, that's very nice, but can you take it out of perturbation theory and scattering amplitudes? Can you apply this more generally? For example, short-chilled black hole. Is that a double copy of something? How about a Kerr black hole? Solutions with cosmological constants, radiation from accelerating black holes, and so on and so forth. And the answer to all of these questions, or all of these examples, is yes, they are double copies. There is a long collection of papers where this has been studied. In fact, the Schwarzschild case is kind of amusing. It's exactly what you might think it is, that it's a point charge in electrodynamics. Why electrodynamics instead of non-abelian gauge theory? This has to do with the fact this is a very simple case. And Andres is going to talk more about that. Now, one thing I should add is there's something interesting happening here. We have many examples, but we do not have a coherent theory. So if you gave me some classical solution in gravity and you say, great, tell me the double copy, I'd say, oh, that looks like a hard problem. Because the first thing you have to do to find this mapping between, let's say, gauge theory and gravity and understand how this double copy works is you have to choose good coordinates. If you choose bad coordinates, it'll be completely obscure. It'll look impossible. If you can choose good coordinates, sometimes it trivializes. For example, the Schwarzschild and Kerr black holes, the key secret is you have to choose Kerr-Hild coordinates. Once you do that, then it's straightforward. Okay, but of course, there's no rule book that tells you what you're supposed to do. You have to have some intuition and some guessing of how to do that. Okay, so in any case, there's no general understanding, but plenty of examples, interesting examples. So one of the applications of one of the original applications, these types of ideas has to do with just trying to understand what people say about ultraviolet behavior of gravity. So the standard lore is that gravity is non-renormalizable. Oh, sorry, I'm having a problem with some background noise. Anyway, the standard lore is that gravity must be a non-renormalizable theory because it has a dimensionful coupling constant, and we can just see this by simple power counting, that if you have a dimensionful coupling constant, then to make up for the dimensions in the Feynman integrals, you just need more powers of loop momentum in the numerator, more powers of loop momentum in the numerator. As p goes to infinity, you get a badly behaved integral when compared to the case of gauge theory. Okay, and you can make various arguments, much more sophisticated about exactly how it works by, let's say, looking at making use of supersymmetry. But at the end of the day, at some loop order, sooner or later, it looks like you're going to run into some trouble, because sooner or later, at high enough orders of perturbation theory, there's enough kappas that something bad is going to happen to you. But the problem is with this is if there's a hidden symmetry, the theory has a hidden symmetry of some kind, or a hidden property or hidden structure, then in fact, this argument is just not correct. Right? Because there could be cancellations between diagrams. For any given Feynman diagram, then this argument is completely solid about how the power counting goes. But you have to worry about hidden cancellations. And I don't mean hidden from the theory. The theory knows what it's doing. It's hidden from us humans. Just hiding in the complexity of gravity. But it's very hard to understand what high loop orders are doing. Okay. And now theory that we like a lot, N equals 8 supergravity. It's really the best theory to study because it has a structural simplicity. We can go to extremely high loop orders and really understand what's going on. And over the years, people have made predictions of where you find these ultraviolet divergences over the years. And maybe as a disclaimer before I start making fun of people for getting it wrong, you'll notice our name. This is Bern, Dixon, Dunbar, and Pearlstein and Rosowski. We also got it wrong. Maybe, okay, but the scorecard, here's a scorecard. So we have the power to calculate. It's not an abstract question anymore. We have unitarity method, we have the double copy ideas. So we can just go ahead and calculate, and we can test predictions. And pretty much the track record is pretty poor. Everything, the first approximation, anything that anybody's ever said about a specific prediction has been shown to be wrong, or there's one that's retracted. There's one that's right, but it turns out this has a curious story about it. The details, the way it works is not exactly, shall we say, as predicted. But in any case, there's something funny going on. Every time you try to, so far you try to predict, look at predictions, things are not, things don't work as expected. This is in 4 dimensions. Now, to be fair, the arguments of why things will diverge sooner or later, they're fair, right? That you're fighting against the dimensionful coupling constant. Yeah.
Sorry, can I ask a question?
Sure.
So what is the deal with 6 loops? Has that been computed?
Oh no, no. Right. No, this one came from a retraction.
Okay.
Yeah, there was a retraction because something else didn't work. Then they retracted. That's right. No. Well, actually, 6 loops is apparently coming. That's what I hear from Alex.
Yeah. Good news. Yeah.
Yeah. But,
thanks.
But you're right. That was not computed. But still, computation drives the retractions. Whenever someone retracts, it's because there's a computation that they start worrying is pointing in a direction that they don't, is contradictory. So then after a while, when they think more about it, there's a retraction. Now, there's actually, here's like a more recent set of predictions. This was after we did our 4-loop calculation. And there was like very definite comments about where things should diverge. Now, one prediction, n equals 4 supergravity should diverge at 3 loops and d equals 4. N equals 5 supergravity should diverge at 4 loops and d equals 4. And then half maximal supergravity. And then there's some other ones. This one is a little bit weird because we go to this funny dimension. Now we say, why did you do that? Why did you go to D? Why is there a prediction in d equals 24/5? Well, the answer is because by this trickery, it's some kind of trickery, you can now make statements about lower loops. If you make statements about too high a loop, n equals 8 supergravity should diverge in 7 loops, then that's really tough. 7 loops is really tough. So you play a game like that, where you try to extrapolate from this, you extrapolate to that, and you say that there should be a divergence. Okay, so there's the predictions, we have the answers. So there's some of them are wrong. We know for a fact because we've done the calculation over the years, various papers. One of them is right. And this one, I have to say, is very disturbing because after all the work at 5 loops, and we did all that work, and of course we were very eager to discover that in fact these people were wrong, let's say Michael Green and all the other people in supergravity were wrong. But then we discovered that in fact there is a divergence here. But maybe I should point out there's something, there's something a little bit naughty about this because we did this, we all focused on 5 loops in this funny dimension. Right? You can ask me, what does that dimension mean? And it's some analytic continuation of integer dimensions. And then you discover that, okay, it worked. But then to add insult to injury, you don't actually know what it means because when we look at the other results, like we look n equals 5 supergravity, and we find that, in fact, it's much better behaved than people had claimed, then you wonder, how is it possible that as you increase the supersymmetry, it gets worse? So what we think the answer is that it's because this analytic continuation is not as simple as we thought. That this is the problem. If you do something unphysical, like you work in 24/5 dimension, something bad's going to happen to you. And there is, in fact, a paper which implies that. They don't prove it, but they definitely show that the unitarity cuts are much better behaved in 4 dimensions as opposed to some funny dimension. Now, of course, what we want is to have a definitive statement. This is what we need. This one, the key question. That's actually pretty tough. But there's Alex Edison. Anyway, he says it's doable, and not only does he say he's doable, he definitely has some progress. Okay. Well, I hope that we get an answer for this in finite time. Okay, now the remaining time I want to talk about an application to the gravitational wave physics. So it's a completely different topic, but same ideas, right? The tools are the same. We're going to use unitarity. We're going to use double copy. And when I say gravitational waves, I mean gravitational waves. We all know the era of gravitational wave astronomy. It's begun. And I can tell you the day I was thinking, I need to work on this, it's just after the original discovery of the gravitational waves. This is actually the original event. When, looking at the papers, it was clear that the power emitted in gravitational waves is more than the power emitted by all the stars in electromagnetic radiation, all the visible stars. That's an awful lot of power. It's basically 3 solar masses disappearing in a fraction of a second, being radiated as gravitational waves. And you got that much power, you think you want to actually understand it. But of course, there's a little bit of a problem. Gravitational waves, it's very far away from our normal hunting grounds of looking at, let's say, supergravity or quantum perturbation theory. So the question is, how can we as particle theorists help out? Now, one realization that came pretty early, like just trying to think about this, is that we're good at gravitational perturbation theory. And in here, to get most of this, just like up from like here to here, like this part, then perturbation theory is used. So you think maybe we can do something. Okay, and so there's 2 problems. One would be, let's say, collider physics. So that's much closer to what we do. So you have particles come in, they collide, and then particles go out. And they're created, and then they go out. And this is based on looking at unbounded trajectories. Particles are coming in from both sides, and then this particle is streaming out. And we use various tools: gauge theory, quantum field theory, QCD, electroweak theory. There's a whole set of machinery of what's done here. This problem, general relativity, it looks pretty different. You're talking about a bound orbit, not an unbounded collision like that. And you're talking about classical physics. So you say, okay, what's the relationship of these 2 problems? Or why is this problem something we can look at? And the insight is actually old. Even back in the 70s, there was Iwasaki, but really systematized by Goldberger and Rothstein. And in a sense, it's pretty simple what's going on. Long wavelength radiation, the gravitational waves are very long wave radiation, 1,000-kilometer scale, much, much larger than the size of the black holes. So if those black holes are very small compared to the wavelength, you might as well call them points. If they're point particles, then okay, then we can talk about it, right? In quantum field theory, wherever we think about particle, it's point particles. Okay, so so in fact, the basic, you could say right there is, in a sense, the essential insight why it might be possible for us to say something about it. And of course, you actually have to say something. I mean, you know, you have to know in detail how to do this. But at least the basic principle of why it might be possible to use particle physics to describe the dynamics, classical dynamics of two black holes, I think that's pretty straightforward. It's just that it's long wavelength radiation, you get a separation of scales, and so on and so forth. And then all the machinery of effective field theory then holds. So what's the idea? We want to improve on the post-Newtonian theory. So we have two black holes, one they're spiraling in, and in the meantime, it's emitting gravitational waves, and then they merge at some point, and then there's a phase called the ring down. These two parts, so we don't have anything to say. The merger, that's non-perturbative. You really need numerical relativity for this part. Ring down, it's a different kind of perturbation theory. Also, this is actually quite accurate. We don't need any help here. At least that's not critical. The critical part where we could contribute something, or there's at least it's the right language for us, is the in-spiral phase. And here you need extremely high accuracy. And the reason is, if you're watching a wave over many, many cycles, let's say you're watching it for 1,000 cycles, very small errors, they build up. So if your theory has a good prediction for a while, then your theory is has small errors, they pile up. So as you head down closer to the merger, then in fact your waveform will be completely inaccurate. It'll be completely out of phase. That's not good. So we need to go to higher orders. And there's of course detailed studies of you know, how the higher orders are contributing, which I'm not going to explain here. But the this post-Newtonian approximation, you could say the problem is straightforward in the sense that we all know the Newton potential. There's Newton, there's a Hamiltonian, there's Newton, and we need to correct it. And the way we need to correct it is through general relativity. So for example, Einstein, Infeld, Hoffman, they computed what's called the first post-Newtonian correction. And that would tell you like import information from general relativity correcting Newton. And the way this post-Newtonian approximation works is we expand in velocity and in Newton's constant simultaneously together, and that makes sense for a bound orbit. Virial theorem says that you expect these to be about the same. And then over the years, people have been cranking this out, and this 4PN is pretty recent, just a few years ago. And people do these calculations not because they are entertained by complicated calculations, although perhaps they are entertained, but it's because it's important. It's actually needed. So you could say that the problem we're facing is, can we use some of the ideas I was talking about? Can we use those ideas to simplify the types of calculations needed for understanding ultimately the waveforms that you see, the gravitational waveforms? And there was, in fact, many people were looking at these types of problems. There's a small industry thinking about, let's say, connections to scattering amplitudes. There's something called world line formulation and how it relates to some of the ideas I was talking about, and some technical questions. But you could say the key question, if you want to be taken seriously, is that you have to answer is, can you calculate something of direct interest to LIGO Virgo, or to the theorists who are working on it at least, decisively beyond the previous state of the art? If you can't do that, it's hard, you know, people aren't going to pay attention, because you have to actually do something very concrete and something, you know, something that shows that it's actually useful. Yeah. So when we started thinking about this, the question we had is what problem to work on. And there's various problems. The black holes can be spinning. Spin is something that particle physicists understand quite well. Finite size effects, that also turns out to be perfectly fine for particle physics. And EFT, in the effective field theory, it's just, we just call them higher dimension operators. So there's a whole language and a whole way of thinking about, say, tidal effects, like you're interested in a neutron star. That would be a good problem to work on. You can think about new physics effects. You could think about details of the radiation, or high orders of perturbation theory. I think you guys know where we're going. Obviously, it's going to be high orders of perturbation theory, because what we wanted was something that needed to be difficult using standard methods. It needed to be of importance to the LIGO theorists. It needed to be relevant for the core mission of LIGO, what they're trying to do, and for future observatories. And it needed to be in a form. We needed to also make it do something in a format that, at least in principle, can enter the LIGO analysis pipeline. Okay. And the answer to that is high orders of perturbation theory, and the specific problem, which I'll explain what this means, is two-body Hamiltonian at the third post-Minkowskian order. Now, it turned out we didn't have to look very hard to figure out what the right problem is, because our friends from general relativity, there was Damour, there's Bonanno gave a very nice talk at Amplitudes 2018 where she laid it all out, told us exactly what we needed to do. And what this slide is from her. And what it represents is, if you look down these columns, they're the post-Newtonian orders. So V square and 1 over R, well, 1 over R really means G over R, would be 0 Pn. So this is Newton. Okay, 1 Pn, that's Einstein, Infold, and Hoffman. And then you march down these columns. Systematically, you go higher and higher. This is where people are. And already this is actually recently, this has gotten under control as well. The post-Minkowski, we in particle physics, we have a different name for it. We call it perturbation theory. You're doing a series expansion, a perturbative expansion in Newton's constant, and you keep all orders and velocity. You make it Lorentz invariant, right? When you do a series expansion in V, in the velocity, you make a mess of Lorentz invariance. So we don't like that. So there was the problem that Bonanno laid out for us. That was the problem to work on. So just to be clear, what we're doing here is we're taking general relativity, and we're going to replace it with a two-body potential of the type that Newton would like, except, of course, we want the higher order terms. And the reason we do that is it extracts, you could say, the physics juice from general relativity, but it leaves all the complexity behind. It becomes a problem that Newton would know exactly what to do with it. He wouldn't have to learn any new concepts. He'd understand immediately what it is. Okay, at least I would think so. Okay, we want to be compatible with general relativity, special relativity, all orders and velocity. We want higher orders, order G cubed, and also I'll talk just a little bit about higher orders. And the way we do this is basically taking ideas from two communities, Amplitudes community and the effective field theory community. And this is laid out in a very beautiful paper. Chung, Rothstein, and Salon basically told us exactly what highway to drive through. We just had to drive down that highway. Okay, and the idea is we take the gravitational scattering amplitudes that we are very good at. There's effective field theory, which then tells us how to extract the potential. And by putting these two ideas together, out come these potentials. And you might think it's inefficient because we start with the quantum theory, and maybe that's a funny place to start. But we are very good at doing these quantum calculations. There's almost magical simplification in the gravitational amplitudes. Yeah? And then the EFT methods, they target the pieces we want. Now, of course, when you start something like this, you discover very quickly all sorts sorts of subtleties and confusions. Here's one that's actually very, very amusing. So if we're working at the lowest order, tree level, it's very straightforward. The translation between an amplitude, there's a scattering amplitude, say from a Feynman diagram, and a potential. What you do is you just take the Fourier transform and you're done, and that's that. And that's essentially the content, and you can find this in textbooks of exactly what you're supposed to do. But if you go to higher orders, very quickly, you start getting confused. For example, in graduate school, I had learned, as it turns out incorrectly, that every loop carries an extra h bar. That is not correct. It's correct if you scale the diagrams the way they tell you to scale the diagrams, but that is not the pertinent question. The pertinent question is, in the physical world, I'm trying to extract a classical scattering or a classical scattering angle from these quantum diagrams. How does it scale with h bar in the physical world? That's the real question. And the answer is, it scales the opposite way they told you. It's backwards. Instead of every loop scaling as h bar, it scales as 1 over h bar. Right? So it becomes singular in the classical limit. Then you go, what the heck's going on with that? But it's not very deep. If I take an exponential, e to the I s classical over h bar, and I series expand, I get higher and higher powers of 1 over h bar. That's all that's happening. But it brings up all sorts of confusion. You can get yourself very confused very quickly about double counts and iteration, because as you series expand, you're counting things that you should have been in the lower order potential. You encounter infrared singularities and so on and so forth, the various issues. And the effective field theory is the systematic way to deal with all this trouble. Okay. And this is the approach we always turn to whenever we get confused, the effective field theory approach. The basic idea is we think about two black holes with a potential. There's a potential. Just an honest to goodness ordinary potential. The two black holes are A and B. There's the kinetic term. The kinetic looks relativistic. Notice it's linear. It's not quadratic. Right? It's linear in time, but that's because no antiparticles. Antiparticles are quantum. We want classical, so this should be our kinetic energy. And from this effective field theory, we go calculate a scattering amplitude. And in that way, we are going to determine what the potential is by matching to the truth obtained from general relativity. Okay, so let me just be, oh, I see I'm probably running out of time. Let me be a little more explicit. So the idea is you do two calculations in parallel. One is complicated, one is simpler. What you do is full general relativity, take out the heavy artillery, amplitudes methods, double copy, generalized unitarity, and you march down and you calculate a loop amplitude in general relativity. You're always looking at h bar goes to 0, so you throw away things that you know are quantum. And then you do a much simpler calculation using a potential based on an ansatz, undetermined coefficients, that you then determine by calculating the amplitude and then matching. If you get a match, that means the physics is identical and the potential describes exactly what general relativity is describing. Yeah. Maybe just a few comments. When we started looking more at this, we discovered we were in unitarity heaven because of two facts. One is that we're only interested in long-range forces, and that effectively means that these gravitons, or the pieces we want, are from where the gravitons are on shell. That we can extract all the physics we need from on-shell gravitons, physical gravitons that satisfy Einstein's relation. And then there's another rule that says that in every loop there has to be one cut matter line, and that's related to the fact that we are actually doing classical. So when you do the energy integral, you better just pick up the residue that says you're on shell. Okay. So there we were in unitarity heaven, meaning the formalism we had, the ideas we have actually matched the problem we're trying to solve. So the idea is you have to now calculate some unitarity cuts. We do recycling. If we want gravity, we start from gauge theory. Gauge theory is simpler. If we want loops, we start from trees. These little blobs are all trees. You assemble it, and you can now go ahead and do your calculation. One little example, let's say I want a unitarity cut for gravity. So there's like a 3-point, a 3-point, a 4-point. And so I put it on shell that's tree level to try to build up this higher order, this loop. I use tree level, and then I use these Kawhi-Llewellyn and tie relations to then turn it into gauge theory. So that's the double recycling. So we're very green. Okay, long story short, we've done state of the art. So this is a calculation that was requested by our general relativity friends, order G cubed, third post Minkowski. This is an amplitude. So this isn't quite what they wanted. But it's relatively compact. It looks complicated, but I'll show you what happens if you try to do it in more conventional types of ways. Okay. And here, this is probably more important. This is the Hamiltonian. If you have the Hamiltonian, you're good to go, because now you can do orbital mechanics. Right now, you can go to the LIGO people. Here's a Hamiltonian. Go ahead, just do what you do. Okay, and once again, this is relatively simple. There's in C1, so this is an expansion in Newton's constant. C1 is Newton. Einstein, Infeld, and Hoffman are the combination of this. You don't quite recognize this as Newton, because remember, this is all orders in velocity. So it's Newton plus all orders in velocity. But if you series expand in velocity, this first term is exactly Newton. Okay. Now you may say, okay, very nice. You're doing all this fancy stuff with unitarity cuts, and how do you know it's right? Well, the basic answer to that is because we could match to the literature. If you series expand in velocity, you can now match up to post-Newtonian. So this is our most important check that we did in our paper, is found the canonical transformation. Remember, if you have two Hamiltonians, they may not be the same, but if you can find a canonical transformation so that the Poisson bracket is preserved, then the physics is equivalent. Okay, and indeed that works. And there are various other checks. There's the best ones are Bini and Damour. Damour especially really didn't like our results, so he wanted to prove we were wrong, but okay, he showed that we did it correctly. So actually, here's something a little amusing. So this would be what the 4PN Hamiltonian looks like. You'll see it's extremely messy, and you're wondering, why is it so messy? And there's two answers for that. One is, if you take a simple function and you series expand it, you make a mess. So if you can resum in velocity, it's simpler. You'll get a nice simple function. Series expanded, it's a mess. And the other reason is there's a gauge choice here. This n dot p, this is like r dot p. There's some terms in here that you can remove under appropriate coordinate transformations or gauge choices. You make a bad gauge choice, it's a mess. Our friends in general relativity apparently liked it. 8 days after our paper, they wrote a paper that maybe I'm out of time, so I shouldn't say much, but let me just say that the conclusion, well, there's no real conclusion, but the conclusion is more comprehensive study. The rather encouraging result motivates a more comprehensive study. And the other request in the paper is more orders of perturbation theory. So anyway, we're happy to oblige. So one question you might have is, okay, this is nice. How does it scale? Is it really a tool that you can keep on going? And we know now for a fact that it is a tool, and that you can keep on going because we've gone. So that's the next order, Q to the fourth. That's a recent paper. It's not complete. Actually, if you're for amusement, elliptic functions do show up here. Luckily, they're the very simplest ones, right? So that was very lucky for us. It's not complete. We're missing some pieces called tail effect that has to do with radiation. But in any case, we published this would be what's called the potential modes, or the potential part of the Hamiltonian. Okay, and I should add that collider physics, all the wisdom that's been collected over the years of all the special functions and how to do loop integrals, we use that. There's a beautiful paper from Parham, Martinez, Roof, and Zhang that explains how to do that. So the outlook is good. There are, I think, many people working on it now. All these different ideas have been touched upon by various people. There's structures like the double copy, and this some interesting thing about the iconal phase, how that works. The state-of-the-art calculations. People are now working more on radiation. There's a nice recent paper about that. There's some beautiful work, a formalism for doing that from Kassauer, O'Connell, and others. There's finite size effects that you can look at in this way. There's a spin that's another problem that's been looked at using these on-shell methods. And I think we're just at the beginning. We're just, the formalism is still pretty new, and I think there's definitely room for improvement, and I think in the coming years there'll definitely be improvement. So the summary is particle physics. It gives us new ways to think about problems of current interest in general relativity. The double copy idea gives a unified framework for gravity and gauge theory. I spoke about sample applications. The web of theories, I think, is something really nice. Tells us relationships between different theories in some very, I'd say, unique way that normally you would think about. And then high loop order calculations in supergravity, especially looking at the ultraviolet. Then some recent work, the two-body Hamiltonians for gravitational radiation. And I think we can expect many more advances in the coming years, not only for gravitational wave physics, but more generally for understanding gravity and its relation to the other forces through the double copy. And maybe I should leave you on right here. Okay, thank you on these papers.
Well, thank you. Thank you very much for this really interesting talk, at least for like a whole new ideas now for general relativity and gravity. We have time for one or two questions, depending on the complexity of the question, of course. Don't be shy, people.
Roger, can I ask a question?
Of course, Lorenzo, go ahead, please.
One very general question. When you do the expansion of the metric in eta mu nu plus the graviton, is there something that can be done when the background metric is corresponds to a curved space?
Yeah. Although that is definitely not as well developed. So there are these papers. I guess Andres will talk about classical double copy, wherever it was. No, not here. But Andres, I think Andres is going to say more about that. Although, yeah. So like the question of, let's say you have a curved space, do these double copy ideas hold? And the answer is just by examples, not a general theory behind it. And then there's other classes of problems that maybe you think about perturbation theory around some background. There's probably been a little bit of work on that, but not so much. I'm not sure if Andres is going to say anything about that.
Okay.
Well, okay. I will just make some comments in my talk, but I can say something more in a couple hours.
Okay.
Right.
But it's certainly a very interesting question about how far you can go, because you know, it's not where, right, you can say at the moment, like most of the work is in you could say the simplest situation of just flat space on shell, and then you really want to know how far you can go. The basic answer, you can go far, but exactly how far is unclear. And like I say, it's case by case.
Okay.
There are people interested in scattering on anti-de Sitter space for aspects of ADS CFT. So I think some of that has been pushed a bit.
Yeah.
Okay. Thank you.
So, is there any other short question? I don't see any raised hand.
That's okay.
Well, if not, let's
In
thank
person would be better.
Christoph Kutak. Christoph, please ask.
Well, I have just a comment that recently there was a paper by Chris White, who studied the double copy, and he just demonstrated that one can kind of prove it in some case using the twistor-based approach.
Right.
So this is physics regulators paper. Very
Yeah,
recent.
sure, but that's still on flat backgrounds.
Yes, that's true. That's flat background. Yeah.
So I'm actually saying something about Chris's paper later.
Okay. So I just wanted to comment. Yeah. Thanks.
Yeah,
Sure,
thanks.
yeah.
Good.
So thank you. So let's thanks once again to Professors V. Bern for this very interesting talk, and we will see you maybe next year in Mexico to all of you. So now if you can, now we have to move to the next speaker, who is Alfredo Guevara. So hi, Alfredo, can you share your screen?
Hey. Yes, I can, but it's in my iPad.
Okay, so now we can start our next talk. This talk will be by Professor Dr. Alfredo Guevara. He is now at Harvard University. And so the title of his talk is From QFT to Scattering Wave Kerr in Kerr. Please, go ahead.
Okay, thank you. Yeah, so I did a last minute change on the title, but it will be mostly about gravitational scattering. And I pretend to give a flavor of some of my current work, but at the same time, I'm gonna go through some computations. So whenever a detail is not clear, please stop me and I can go over it with more detail. Okay. So just to give you a brief motivation. So let me just mention two problems, two current problems in gravity and in high energy physics. The first is a gravitational problem, and it's about the perturbations of the Kerr metric. So we all know and love the Kerr metric because it's an exact solution for an isolated spinning black hole. So in that sense, it's kind of miraculous. there was no need in principle for such, there was no underlying reason in principle for the existence of such an exact solution, but we have such a solution, and we believe it describes most of the astrophysical black holes that are present in our universe. So when you have this this mathematical description, one of the first questions you may ask, and it was asked a long time ago, is about the stability of the solution. Is it actually stable? What happens if we perturb the solution? What happens with, you know, if we throw a small perturbation, say a wave, does it get damped at late times or not? Do we recover such a Kerr solution, or we find something else? And this question is only formally answered for the case of Schwarzschild, and it's actually under study whether such solution is stable. But lots of physical and mathematical tools have been developed so far regarding the stability of the Kerr solution. So one of them is a quasi-normal mode description, absorption, and the description of the love numbers for spinning black holes, which are tidal responses to certain perturbations. Okay, so it's the analog of the electromagnetic susceptibility for this kind of sources. Okay, so there's a lot going on for the Kerr for the studies of the Kerr metric, but there's also another interesting topic, which is the problem of interacting higher spin particles. So, well, just to give you a rough description, because of string theory, we know that these kind of particles can actually interact in a consistent way when you have an infinite tower of them. Okay, so meaning particles of arbitrary high spin, integer or half integer arbitrary high spin. But if we truncate such a tower, say we keep just a finite number of such higher spin particles, there are several inconsistencies. There is some problem with causality violation. So if you consider an effective field theory of gravity, say corrections to Einstein-Hilbert action, you will find that there is a need for including higher spin particles, but at the same time you have to include the full tower. It is not possible to truncate it. And also we know certain description of higher spin particles because of the effective field theories such as bound states on QCD. Okay, so higher spin particles are currently an open problem, whether they have a non-trivial S matrix or not, meaning whether they interact or not. And what I want to advocate here is to propose a link between these two seemingly unconnected topics. And I want in particular to provide a flavor of what computations we do in order to establish such a connection, okay? And the connection can be read roughly as follows. Meaning is that the Kerr black hole can be identified in a certain sense with a higher spin particle, okay? That is consistently coupled to gravity. And when I say consistently, I mean that there is a non-trivial S matrix associated to such a particle, okay? So this is just a single higher spin particle, not an infinite tower of them. Okay, so that's it for the motivation. Now, let me just introduce some of the tools that we will be using. Okay, so to start with, consider a minimal coupling amplitude. Okay, so this is going to be a 3-point amplitude. Okay, so I'm sure there are a lot of new ingredients in these slides. I promise if you follow it carefully, it will pay off. But please stop me if there is something unclear. So we have a 3-point amplitude, and this is 3-point amplitude couples two states, which are spin S states. Okay, so the first one I described with this state epsilon 1a, and the second one with this state epsilon 2b. Okay, so there are 2s plus 1 of them. I messed up here, and it couples them to a graviton which has helicity plus or minus 2. So there are 2 states in this case. Okay, so a graviton is described by a tensor with 2 indices. This is spin 2 field. It can factor in a way that it's reminiscent of this double copy idea that SV was also mentioning, into 2 polarization vectors. Okay, so I'm going to take one of these polarization vectors and I'm going to construct the field strength. Okay, the field strength in momentum space. Remember, the polarization vectors satisfy this relation. This is just gauge invariance statement. And using this field strength, I'm going to construct an operator here. So J mu nu is going to be a Lorentz generator. Okay, that means acting on, for instance, a spin S state, if we take S equals 1, is going to do a Lorentz transformation. Okay, so it has 2 free indices. I contracted with this field strength that I just constructed, and I divide by this quantity here. Notice that P1 and P2 are massive, whereas K is massless. So using this, you can actually see that this is a gauge invariant quantity, and it's in fact a 3-point amplitude. Okay. Okay. So I take this exponential, meaning, you know, this is an operator, and I have to expand the operator. I exponentiate this operator, but because I'm considering a spin S representation, that means the operator, the exponential itself, is going to truncate. Okay, it's not really an infinite series. This happens because of the fact that I have a finite dimensional representation. Okay, so actually, if you take, let's say, a matrix and you take it to a certain power, you know, you will eventually recover the identity and lower powers. Okay, that's the Cayley-Hamilton theorem. So this exponential is actually not an exponential for a finite representation, and in fact, you can check that it will truncate at an order 2s. Okay, so I only need to expand this exponential to 2s plus 1 times. So here's an example. If I take a spin 1/2, meaning what it means is that this this exponential is going to be acting on spinors. Okay, let's call them U1 and U2. If I take such a spin, what I'm going to get is only 2 terms. First one being the identity, and the second one being what's called dipole coupling. Okay, between a field strength and a Lorentz generator, which in this case is a Dirac matrix. Okay, so these are the elements in play. What I have so far is a 3-point amplitude that I claim corresponds to a minimal coupling. It's constructed more carefully in this reference that I gave here. But the statement that I want to convey today is that this weird-looking exponential actually contains all the information of the linearized Kerr metric. Okay, so if I take you know, my Kerr metric and I linearize it, meaning I'm only going to keep the order G term. Okay, go to harmonic gauge, I find that it has a similarly looking exponential structure. Okay, so I have the Newtonian piece, it's actually the Schwarzschild the Churchill potential. But because I include a spin, so a spin here is parameterized by some kind of a spin vector, okay? If I include a spin, what happens is that I get some exponential correction to my Churchill metric, okay? And this exponential correction is encoded in derivatives acting on the Churchill case and contracted with the spin vector, okay? So here yes, the norm of this vector is actually the ring singularity radius of Kerr. Okay, so this is a fancy way of writing the Kerr metric. And if you go to 2,2 signature, basically you can resolve this Koch and Sinch, and you in fact find up to a sign that this is precisely an exponential. Okay, so in a sense, you're kind of boosting the Churchill case into the spinning case by applying this operator. So this P here is for momenta associated to a spinning particle in the rest frame, of course, because we're considering a stationary solution. We're going to take P to be this unit vector. Okay, so that's the rest frame. So this is the standard frame you would use to describe the Kerr black hole, but we can consider a more general P, because this is just a frame choice. So I'm only going to assume that P squared is just on shell, and that means U squared is just a unit vector. Okay, I'm not going to assume this kind of frame. This metric still makes sense. Now what remains to be answered is what's the relation between this 3-point amplitude here that I just described in the previous slide and the metric the metric obtained from a stationary singularity, okay, that has 4 velocity P. Okay, so this would be the metric sourced by such a singularity. Okay, so both have this exponential structure, but you may ask what's the precise relation between both. Okay, so the first step, because the amplitude has 2 massive momenta, we want to identify one of those with the actual momenta of the black hole. Okay, the actual P, and we can take, for instance, the average. At this linearized order, it doesn't really matter whether I choose the momenta of the black hole to be P1 or P2 or the average of those. I'm always going to get the same description because there is no back reaction from any other source. So I can take, for instance, the average, and that I declare is my 4 velocity. Okay, my classical 4 velocity. Okay, so the way I can think of this is, I'm coming from far from past infinity. I scatter some gravitational field, and then I go to future infinity, and this all makes sense only in 2,2 signature. But nevertheless, it provides a matching description to the Kerr metric. Okay, so let's compare the exponential. I told you that this 3-point amplitude has the exponential of the angular moment, the Lorentz generator, whereas the Kerr metric has the exponential of some spin vector. Okay, so in principle they are very different. Okay, this is the Kerr metric, and this is the 3-point amplitude. Okay, so the first thing we do, we take the Lorentz generator and we decompose it because Lorentz generator is an element of SO3, 1 algebra, and we know that algebra has two pieces. It has first rotation generators, and it has boost generators. Okay, so of course these two pieces are not independent. Boost to transform under rotations, but nevertheless we can write this as some semi-direct product at the level of the algebra. It means basically we can decompose a generator into two parts, this direct sum of two parts, and the boost is defined this way. Okay, so this is the reason I actually need, some reference for momenta or for velocity, because this decomposition can only be done with respect to a frame. And in this case, I'm going to take u, the vector that I defined previously, to be the forward velocity of the black hole, to give me such a frame. So once I do that, I decompose this into S mu nu, and basically this is S mu nu is just defined as the difference between, my Lorentz generator and my boost generator. And I can compute the algebra of these generators, and I find, okay, it's a SO3 algebra. And the fact that, it's a rotation means it's going to act trivially on my forward velocity. Okay, so it preserves the direction of my forward velocity. Okay, and that condition can also be phrased as this constraint, which is also called sometimes spin supplementary condition. Just in case you want to make contact with some of the classical literature. And the boost generator, it doesn't preserve, of course, the direction of u. And there's some kind of interplay between rotations and boost that I'm going to describe now. But first, let me just mention that instead of using this tensor here, S mu nu, as the generator of rotations, we can basically dualize, because this is a it's a 3x3 antisymmetric matrix in the rest frame of U, so we can dualize it to a vector, and such a vector is called a spin vector. Okay. Now this spin vector in quantum field theory is also called the Pauli-Lubansky vector, that is used for classifying spins of different representations of the Lorentz group. Okay, so it's the same in this way. In the way I constructed is precisely the Pauli-Lubansky vector of the spinning particles, but at the same time it also corresponds, and you will see now, it also corresponds with the spin vector of the Kerr metric. Okay, so this is the element that is going to enable me to perform the matching computation. Okay, so let's go through the computation itself. We first recall that a graviton has two helicity states. Okay, I call them plus or minus. Recall that graviton polarization is written as a direct product of spin 1 polarizations. Remember the definition of the field strength, and whenever I choose a polarization, I choose a chirality for my field strength. That's basically the definition of what helicity means. If I choose a plus polarization, okay, up to some convention, I'm going to be choosing a self-dual field strength. If I choose a minus polarization, I'm going to be choosing as anti-self-dual field strength. Yes. So what happens now is that because of the fact that my field strength is self-dual, I'm gonna be working with a self-dual Lorentz generator. Okay. So remember, my 3-point amplitude is the contraction between F and my Lorentz generator. I split my Lorentz generator into a spin part and a boost part, as I just showed. And then I use the self-duality condition on my field strength. And what I find, if I consider my generator to be self-dual, basically the boost part defined in this way precisely agrees, because of the self-duality condition, precisely agrees with my spin vector. Okay, so these two things actually mix, and once we choose this chirality, we cannot longer distinguish between rotations and boosts. They are mixed. Okay, because of the fact that I choose my generator to be self-dual. Okay, so now using this result, I plug it into my 3-point amplitude, and I find, okay, it actually simplifies, because there is only one generator. There is no spins and boosts. There is only the generator of rotations. Okay, so the Pauli-Lubansky vector is just a name for an SO3 generator. Let me just make that. So if you actually compute the algebra of these vectors, you find that they satisfy the SO3 algebra. Okay, that's what I mean by generator of rotations. And once we have this form, well, trivially you expand F as, the field strength, and then one term cancels, you get this term. It's just 2 times k dot a. Now this is starting to resemble the exponential of the Kerr metric, except that there is a factor of 2. Remember, if you recall this expression, this would be something like a dot k, because it's some derivative, so it's some momentum. But here, the thing we obtain from the 3-point amplitude has this factor of 2. Now, this factor of 2 has an interesting explanation. Unfortunately, I don't have time to go through. But once you align these two momenta, P1 and P2, with my 4 momenta U, remember that U is the average between these two. So if you align these two states, which are polarizations for P1 and P2, if you align them with respect to this average, basically this will compensate for the factor of 2, and you will find actually there is no factor. Okay, so the take-home lesson is that at the very end, when we align everything with this reference momenta, the 3-point amplitude, first the rotation part and the boost part of the generator combine. Okay, so we get something that only has powers of the spin vector. And the second thing is that we do get the correct factor. Okay, and the fact that you get the exponent only to depend on the spin vector is not trivial at all, because we started with something that was Lorentz invariant, not SO3 invariant. Okay, and at the very end we found that it only depends on SO3 generator. So this was some kind of accident, but it had to happen in order to describe the Kerr metric, because the Kerr metric is constructed using powers of the spin vector. Okay, so this was a point that was made clear a couple of years ago by some people in the effective field theory, in the effective field theory framework. Okay, so just to recap so far, what we have done, we have introduced a 3-point amplitude that had a funny exponential structure. We wrote the linearized Kerr metric in a funny exponential form in 2,2 signature, and we claim that, okay, these two actually are the same exponential. An explanation for that is, of course, you can regard this tripping amplitude as some kind of correlation function for a source. In this case, the source would be some stress energy tensor. And this is just the classical argument of the LSC reduction. And once you take the source, you Fourier transform in 2,2, basically you get the field that it sources. In this case, that would be the Kerr metric regarded a certain graviton. Okay, but so far this is all weird, and the reason is weird is because, okay, we actually need to go to 2,2 signature because, well, scattering amplitudes only depend on radiative modes, and because Kerr solution is stationary, there's no radiation. So matching a scattering amplitude with something that has no radiation, it's not natural. Okay. In a sense, the Kerr metric, as you can see from this dependence, is contained in Coulombic modes. Okay. Whereas in this case, we're computing radiative modes. So these behave different as you approach to asymptotic infinity. Now, this only happens for this single isolated Kerr black hole. Okay. But if we do perturb the Kerr metric in 3,1 signature, okay, we indeed find radiative modes. So you may ask whether those radiative modes are in correspondence with 3,1 scattering amplitudes. There are two kinds of interesting perturbations that we can consider. The first one is perturbations of, wave perturbations, such as a scalar wave, an electromagnetic wave, or a gravitational wave, which you may suspect is the most interesting one. And also another kind of perturbation is nothing but the duality problem, because the way as SV was mentioning, the current way the two black hole problem is being attacked is to consider a perturbation theory of a single black hole problem. So this is roughly what effective one-body formalism is about. So interesting things happen when we consider perturbations of the Kerr metric or even the Schwarzschild metric. And even more interesting is the fact that these perturbations consider radiative modes, and these radiative modes are contained in the computations of the scattering amplitudes. So for us to see the matching, we need, of course, to consider higher point amplitudes. These are two examples. So the first example is called Compton scattering because of historical reasons, but it describes, in our context, what it's going to describe is just throwing a wave to my Kerr black hole, which is this massive line here, and see how the black hole reacts. Okay, so far this is the simplest extension of the matching that we can write down. Okay, now in order to encode the radiative modes of the perturbation of the metric. Okay, so now I want to perturb the Kerr metric. What's been used historically is called a Newman-Penrose formalism. It's a way we can describe asymptotic non-infinity. And in our context, basically in the context of linearized gravity, what I'm going to need is only the description of the Minkowski metric, okay, which is going to be the background of my perturbation. So I split my Minkowski metric into two parts. These are all, M bar, L, and N are all null directions, and they satisfy this condition. So they are conjugate in a sense to each other. And I should think of L as my direction pointing towards, it's a direction in the celestial sphere. Okay, so if I have Minkowski spacetime, L would be a null vector pointing from the origin to a certain direction in my celestial sphere. And it might sound far-fetched at first, but it turns out that this L, besides being a null direction, I will interpret it as a massless momentum. Okay, so I'm going to write down a relation between K, a massless momenta, and a null momenta, and L, and the coefficient of those I call energy. Okay, if I take this seriously and I read L, besides being a direction, is a massless momenta, then I find very easily that M and M bar, which are directions on the sphere. So I'm not sure if I can even draw it, but M and M bar are nothing but directions on my celestial sphere. I find out that these are, or this can be thought as massless polarization vectors associated to K, because of the reason that, well, they satisfy something like this, right? So in a sense, they are polarization vectors. So, okay, so once I have these tools, I construct my Newman-Penrose scalar or my Weil scalar. I consider my Weil tensor, and I extract a component, which is Lorentz invariant. This component quantifies the flux of radiation that's going through celestial through the celestial sphere. Okay, and this is a very it's a textbook computation, but let me just sketch it. I didn't even write the details, but what's important here is that as we go to asymptotic region, so as we take x to infinity, so, well, to be honest, the norm of x to infinity, but we go through a light cone. My radiative field is gonna be, if I decompose it in Fourier modes, so I write, Fourier modes of my radiative field as this source. So in general, this would be, because I have some propagator, there would be a k squared downstairs, but because of the fact that I'm computing radiation, there is a delta function. Okay, so I'm going to consider on-shell momenta when I do this Fourier decomposition. And what happens is that as you go to asymptotic region, basically this integral localizes in a funny way. It localizes over the region such that K, the momenta of the modes, is parallel to the direction of observation. Okay, so X here, which is in the asymptotic region, has some direction, which I call X hat, and the spatial part of K has to be parallel to that. That's the saddle point approximation for large radius. That's what it tells me. So it tells me that my radiative field is only going to have modes contributing over the light cone that connects, the origin to the celestial, to the point in the celestial sphere. Okay? So that's just a very fancy way of saying, basically K, the mode of the source is going to be proportional to L, which is the direction of the celestial sphere. Okay, which is what I was anticipating here. Okay, so this happens for the radiation. Okay, the radiation modes. Now I take this formula and then I compute the Weil tensor of this metric, and it has many parts, but it has two derivatives, of course. my source. At the very end, I have to hit it with these 4 vectors here. And what I find because of this identification is that, well, every time I have an N with a K, that's just gonna be 1 because, because of this condition. So these 2 N's are gonna be contracted with 2 Ks, and what is left is gonna be M bars contracted with T's. So M bars are polarization vectors, and at the very end, I get this contraction between polarization tensor with my source, and that again is again using this standard LSC argument. I have a source now, and I want to contract it with just extract some polarization component. I identify this with certain scattering amplitude. Okay, so what scattering amplitude precisely? It depends on the process that I'm considering. If I'm considering the scattering of a gravitational wave, this is going to be a 4-point amplitude where a gravitational wave scatters with my background. Okay, here the background is going to be described by some massive higher spin particle. Okay, so this is roughly how the matching goes for higher point amplitudes, not only 3-point amplitudes. And this is completely Minkowski signature. So this is actually the physical process of scattering in a Kerr background. Okay, so now the question that you may ask is how do actually we obtain these amplitudes? So the 3-point amplitude, I told you, well, there is some reference for that. But in reality, it can be fixed by some criteria. I told you it's minimal coupling, but this is not quite the sense in which we learn the minimal coupling in undergrad, but it's a slightly different condition. The condition is that if I have a massive amplitude and I take large energy, sorry, yeah, it's in a sense a large energy limit. Okay, so I boost my momentum to infinity, my massive momentum to infinity, or I take the massless limit, take my mass to be very small. This should become, this should be well defined. Okay, so unless my effective description of this particle breaks down, in which case I don't have any control, I expect this to match a certain massless amplitude. Okay, whenever I take this massless limit. And it so happens that for 3 points, these massless amplitudes are all known and fixed. There's only one such amplitude for a given helicity combination. So for instance, if I take massless limit of spin S particle, then I'm gonna get a 3-point amplitude of helicity plus or minus S and a graviton. So this 3-point amplitude is massless and it's known. This has been fixed completely. You can check out this book in order to have some reference for that. But what's very nice is that there is only one answer I can write in this side that gives me the correct one on the other side. Okay, so there's only one massive amplitude for a given massless one, and that completely fixes my massive amplitude and is equivalent to certain constraints that people found a long time ago for causality of higher spin, or no superluminality constraints on higher spin particles. Okay, so this all works very nicely at 3 points. So this is exactly what the amplitude I showed you before. It has this exponential. What happens at 4 points? Well, for 4 points, if you take a particle of helicity up to 2, so for instance, a graviton, this amplitude still makes sense. So I can do the same trick. I can take my massive amplitude for spin 2, and then take the massless limit and impose that I recover the massless one. Okay. Once I do that, again, there's only one there is only one massive amplitude that matches the massless one, and you can write it in this way. It's exactly the same as we did before, so that's very nice. The exponential structure appears again. Nevertheless, remember that because of the fact that we have a spin 2 particle here, this exponential truncates only, it truncates at the fourth order. Okay, so it's not really an exponential. And we play the same trick, and we write down this J in terms of A, the SO3 generator. Okay, so this works very nicely at 4 points up to spin 2. For higher spin greater than 2, these massless amplitudes are not known. They're actually inconsistent. There's no such thing as interacting S matrix in this case. So whatever the massive amplitude is, we don't know, because we cannot use this criteria. But this is currently under investigation. We have learned a lot of how these amplitudes could look. Okay, but so far there's no definite answer for this case. Okay, so we can only work up to spin 2. But this is enough, because you see the structure of this exponential doesn't really care about the spin. So if I take a spin 3 or a spin 100, I'm always gonna get exponential. What really changes is, it truncates at lower orders, but at least the first orders should coincide with the Kerr black hole, even though I'm looking only at the spin 2 particle. Okay, never mind that one. So we have argued, I hope, that the 4-point amplitude should match to a certain Newman-Penrose scalar. And I told you an argument for that to happen, but now you may ask, okay, this computation maybe can be done also on the classical side and is more straightforward. Well, it's not. It's actually more complicated, and it's actually takes a lot of work to do this computation on the classical side. But in some cases, in the simplest case, it's obvious why these two things are going to match. Okay, and let me just show you the simplest case before I run out of time. The simplest case is not Kerr, it's Schwarzschild. Okay, and it's not a gravitational wave, but a scalar wave. Okay, so in this case, I take this 4-point amplitude. Again, I have this massive particle here, but this guy is a scalar now. It's not a graviton. Okay, and this only has a single Feynman diagram where there's some gravitational interaction happening between the scalar and the massive guy. Now, what would you do? You want to scatter a scalar of a Kerr black hole while you solve the Klein-Gordon equation. So that might seem simple, but it's not, because this is curved spacetime now. So you have to expand G into 2 terms. So this term is now the Schwarzschild metric. And if you assume some conditions, some gauge condition, the harmonic gauge and the tracelessness, you're going to find something like this. Okay, so this starts looking relatively simple. I simplify it a little bit just to make connection with what I want to do. I just Fourier transform. I consider a single mode of definite energy, and now it looks like this. Okay, so this is the way Klein-Gordon equation would look like. I want to solve it in the scattering case, but first let me just point out that now this very much looks like a Schrödinger equation. Okay, now this is an important point, because I started from a classical equation, Klein-Gordon equation, solving Klein-Gordon in Schwarzschild. And now I find out that there is some connection to quantum mechanics. And I can describe this as a Schrödinger system where there's some coupling given by the gravitational field. And if I want to do scattering in quantum mechanics, I know that I have to consider an incoming wave coming from past infinity and a scatter wave. So my incoming wave is going to be plane, just a plane wave, and my scatter is going to be whatever I get from my scattering. And I consider the Bern approximation, to leading order in G. And what happens is that incoming wave just appears on the right-hand side, because of leading order, this is in the kernel of this operator. So the incoming wave appears here, the scatter wave appears here, and this becomes the Helmholtz equation. You can solve it just using Fourier transform. Okay, and again, you can assume, because we're considering scattering, that I'm going to look at the asymptotic region. And if you look at just the ratio between these two, that in quantum mechanics it's called scattering amplitude, you find out that it's given by this quantity. Okay, so I'm just solving the Helmholtz equation for an incoming plane wave, and I find this. Now, this very much corresponds to a Feynman diagram, because if you look at it carefully, what you're doing is basically just taking the Schwarzschild metric, Fourier transforming it, and hitting it with some vertex. Okay, so if I write down the interaction like this, what I'm doing is considering a Schwarzschild metric that I obtain from just a massive particle, and I hit it with my 3-point interacting vertex of two scalars and a graviton. Okay, so this is on the nose. It's a single Feynman diagram computation, and I did it starting from my Klein-Gordon equation. Okay, but on the way we went through the actual Schrödinger equation, so that is at least curious, and at the very end we went through relativistic quantum mechanics or quantum field theory, and we found out that it's actually a Feynman diagram. So there are at least 3 stages in this matching. Okay, so now just to go through the summary of how it goes for higher helicities and higher spins. For ways that carry helicity, the analog of this computation, the Klein-Gordon equation that models a scalar perturbation, is called the Rayleigh-Wheeler equation, at least for certain parity, and it controls perturbation. It's universal in the sense that you can do a scalar, but also neutrino, gravitational, and electromagnetic perturbations of your Schwarzschild metric, and you get such a simple equation with this potential. Okay, so the only thing that changes is the potential, and then you solve it using the way you solve this kind of differential equations. You do separation of variables. The angular components really don't matter. These are just spherical harmonics, but the radial component. So this is the way the perturbation is written down, such that we get to the actual Rayleigh-Wheeler equation. Okay, so the angular components doesn't really matter. You get some quantum numbers here, but at the very end, you want to study the radial components. So it's effectively 1D scattering. Okay, and the thing you might notice is that this Rayleigh-Wheeler equation, it very much looks again like the Schrödinger equation after you do these rescalings. So you have to scale the energy with h bar, the radius with 1 over h bar, and you have to leave this quantity fixed. So this is the kind of scaling we need to do in order to go from quantum to classical. So if we're gonna solve the Schrödinger equation, we can use this limit in order to obtain the Rayleigh-Wheeler equation. Okay. So then there's some second quantization procedure in which, instead of having the black hole, and this was done, of course, in the framework of quantum mechanics, we know that instead of scattering, a wave function with a source, we can replace that source with a particle. Okay, so this is all what I've done so far. Instead of considering a source, in this case a black hole, I replaced that with a particle, and this dictionary gives me an argument for doing so. And the argument is that I'm just translating between quantum mechanics and quantum field theory, and this should agree in this non-relativistic limit. So this just demonstrates that I can consider 4-point quantum field theory amplitude in order to describe the scattering process in Kerr. Now, we can extend this dictionary because so far I was talking about Schwarzschild. Once you put the spin in the game, there's a spin vector now. The Reye-Wheeler has to depend somehow on this spin vector, and it has a name. It's called the Taukovsky equation. It's more complicated, so I'm not gonna talk about it, but let me just mention that the same separation of variables takes place. So instead of having spherical harmonics, I now have spheroidal harmonics, and this is not trivial. It's really miraculous that we can again do separation of variables in Kerr. And this is again one of the miracles of this nice metric that, since things seem to be integrable in a certain sense, we again have this angular dependence completely integrated in this case. And again, the problem is going to be 1D quantum mechanics for finding this function R. Okay, so instead of, when I go to quantum field theory, here I put a Kerr black hole, and here I put a spinning particle instead of a massive scalar as I was doing a second ago. And instead of a massless wave, as I was doing before, I put, of course, a graviton or a photon or whatever I want to scatter with this black hole. Okay, so the graviton is, of course, an interesting case because it tells me about the scattering of gravitational waves. So I don't have much to say, just to mention that it actually agrees if we consider the 4-point amplitude that I showed you before, and with these scalings, as I argued recently. And if we actually take this amplitude and expand it in spheroidal harmonics, we agree with the computation of, these Newman-Penrose scalars. Perfect agreement up to spin 2. Okay, so that means that this amplitude that we found, let me just pull back a little bit and just remind you that this amplitude we found just for the 4 graviton amplitude, using this minimal coupling criteria, we found out that there's this exponential. So this we got for free. There's no computation here, except that, of course, there's some rewriting that we went through, and it's a little bit painful, but roughly this amplitude, as SV mentioned, we have completely controlled, and we didn't do any computation. Okay. On the other hand, the computation of solving this Klein-Gordon equation or the Reye-Wheeler equation or the Taukovsky equation, which I didn't even write, is a new computation, and it actually hasn't been done. So this provides a very nice matching between these two approaches. Okay, yeah, I don't have much more time, so let me just mention a brief outlook or summary. Well, there's many things to do, but I'm just gonna say that the scattering of waves in Kerr and the Kerr metric itself can be mapped to scattering amplitudes, okay, that involve massless particles and spinning massive particles, okay? So there are some subtleties that I didn't go over, but you may ask what happens with Coulomb dragging. Are these massless states actually free and asymptotic infinity? There are some effects that we need to incorporate, of course. And what happens with gravitational wave scattering? Well, you have these 3 diagrams that you need to consider. It's not as in the case of the scalar scattering that had only 1 diagram. So that actually has certain implications. Okay, so whatever we do at higher spins, if we do a higher spin computation, is this gonna be defining a consistent interactingness matrix? Is this actually consistent with unitarity? So that there are many tests that one can do. So far, we haven't found any test that actually discards these amplitudes, but you may run a lot of tests for unitarity. For instance, superluminality or time delay tests can be used to impose this constraint. And finally, let me just mention that this 4-point amplitude that we associated to gravitational wave scattering can be also implemented in other contexts. So that's why it's actually very useful. For instance, in the two-body problem that SV was describing about what was describing, this amplitude play an important role in the 2 p.m. computation. So yeah, that's all I wanted to say for today.
Thank you. Thank you very much, Alfredo. It seems like it is a lot of work behind that. So it's a pleasure to have this very interesting and nice talk. So now we open to questions, comments.
Have you looked at other spinning interactions that go beyond Kerr? There's a paper called Silence of Binary Kerr, which argues that spin entanglement is minimized for the Kerr interactions. I wondered if your perspective sheds any light on that.
Yeah, that paper is, as far as I know, is using the exponential amplitude that I showed. So, well, that one is fixed by minimal coupling. So, in a sense,
they study non-minimal couplings, I think, and they look at how much they quantify some spin entanglement, and they argue that it's minimized for minimal coupling. But they also study non-minimal in order to know that it's minimized. You have to compare it to something else. So there's some non-minimal couplings in there in the calculation.
Yeah, that would be interesting. So far, I personally haven't looked at non-minimal couplings. Yeah. So, yeah.
Okay. So please, Zvi, if you can.
Alfredo, that's very nice. Do you have some insight on this criterion that you use, where you're matching to them? You have a massless spin 2, and then you want it to be smooth in the massless limit, and then out comes an amplitude that's good, as opposed to not doing that, and then there's problems with causality. And do you understand what it is, like some insight of why it works this way, that this is the right thing to do, like a simple explanation of that, or it doesn't have to, well, it doesn't have to be precise, but just some intuition?
So you're asking why the massless limit avoids the problem with causality? I mean, the massless...
So when you do the massive amplitudes,
Yes.
and let's say the massive spin 2, the Compton, and there's a particular choice you're making for how you're defining that. There's an ambiguity, and it's like a magnetic moment term. And if you pick the right one, right one means smooth. It's like, yeah, this P goes to infinity, that it matches smoothly, then everything is fine. If you don't do that, it's not fine. But do you have like some understanding, like an intuition, why that's true? I mean, other than, there's some calculation, and then you demonstrate some causality violation.
Yes. So yeah, this question has been around for a long time, and the answer is, of course. So we expect that this describes an effective field theory that's good at is good as we take this massless limit. But I mean, up to spin 2, because we know particles of spin 2 can be massless. So for higher spins, really, we expect it to break down. So there is no such thing as massless limit. But up to spin 2, if we trust this as some effective field theory, we know that in the high energy, it should behave as this 4-point massless scattering.
That is right. That is true. You would expect that. Okay.
And we know, and we know 4-point massless scattering is unitary, so that's probably a way of saying somehow unitarity should be present.
Okay.
Okay, so last question, because otherwise we will not have the coffee and the picture, from Gilbert Bautista.
Yeah, hi Alfredo. So I just have a simple question. So you mentioned this non-relativistic limit of, but is it actually a non-relativistic limit? Because Reggie-Wheeler equation is still relativistic. So is it more like a low energy limit?
You mean this?
Yeah.
Yeah, I mean, well, here what I was talking about, how you would go from these two processes, but these are both quantum processes. In order to keep h bar finite, you need to take c to infinity. But what I meant before, of course, is not the quantum scattering. It's a regular scattering, right? So in that case, you can take h bar to 0, and it's also the same. You get the same limit if you take h bar omega to 0. So that's some kind of classical limit.
But it doesn't have anything to be non-relativistic, correct?
No, c can be finite. Yeah, so you can set c to 1 but take h omega to 0.
Okay, so now we have to thank Alfredo once again for this very interesting talk. And so before going for the coffee break, can we just only turn on our machines and then to take the picture of this meeting? So I think that Mario is going to take the pictures.
Yes. Alfredo, could you stop sharing your...
The thing is the US doesn't have a very long range budget process. It's really only good for 1 year, and then you have to go through it again. And oftentimes there are, arguments, and there's the budget there's a big crisis near the beginning of the next fiscal year, and there isn't a budget passed. And they pass something called a continuing resolution. And then you're just operating on what happened before and not really the next year's budget because it hasn't gone through yet.
By the way, about this snow mass planning, is the people in Amplitudes getting involved, or is mostly phenomenology and collider?
Well, Svi should answer that question because he's in charge of,
The answer is yes. So this was the first year that this has happened. So, I mean, when I heard about it, I was very excited. It's like, wow, Amplitudes is a real field now, because it's treated as an equal among the various fields of theory. The slightly unfortunate thing is because of the pandemic, the whole process got delayed 1 year. So nothing's going to happen for a while.
but also all of theory is supposedly being treated as a frontier, like the experimental frontiers. Now, I don't know what this will mean, because SNOMAS is usually a forum for experimentalists to agree on big projects where they need to get some kind of consensus. And it doesn't exactly work that way. The consensus is much more grassroots, and people just go at different rates to different areas, or at least fundamental theory. I mean, so anyway, it's supposed to feed into the funding process, but what it means for theory and funding isn't so clear yet.
That's right. And what it means for Amplitudes is less clear. I'd say ultimately at the end, all the commotion and all the work people do. So people spend a lot of time writing white papers and letters of intent, and there's a lot of work. And at the end, there'll be a final report. And the most we could possibly hope for is the word amplitudes is mentioned somewhere as one of the interesting areas, and that's it. But of course, it sounds like very little for a lot of work, but on the other hand, that could be very powerful to even have a simple mention. And also theory in general, I mean, more than just our local interest, just more generally, just that theory be mentioned in a paragraph saying the importance of theory and its connection to experiment. And if that paragraph is not there, that could be trouble. So there's a lot of work to get these basic paragraphs in.
If you look at how theory is treated in like the European strategy report and compare with what happens in US planning reports, I think the theorists in Europe have done a better job of raising awareness of the importance of theory.
Great.
Or the experimentalists are more enlightened there, I don't know which.
Okay, now we have to continue with the talks. So now we have...
Wait, you have to wait till Andres gets back.
Oh, where is Andres? He's not here.
He left for a second, it looks like.
Wait a few seconds, Roger.
I was looking at Andres. He was the only one who really went for a coffee, and his mug is from Mexico City. If you look carefully, it's one of the coffee. And so the mug says Mexico City. Really, right? I'm doing.
Yes.
Now, okay, let's continue with one other friend from this meeting, which is Andres Luna, who is now in UCLA, and he's going to talk about aspect of the classical double copy. Please, Andres.
Thank you. So let me join the other speakers thanking the organizers for putting together this nice remote meeting. Of course, the hope is that next year we will be able to meet in person, but anyway, it's great to hear from you and to see everyone else here. So as I said, this is the second installment. Last year we met in Mexico City for that new trends in quantum field theory. Now they expanded the title, so now it's new trends on QFT and amplitudes and gravity, which is good because this talk has nothing of QFT or amplitudes. I will now focus on some classical gravity. So what is my outline? I will first review the Kerr field double copy. Then I will tell you a bit about that other incarnation, which is the Weil double copy. And I will tell you something about some cool new stuff. So the nice thing of speaking after Zvi is that I don't need to motivate anything. I don't need to introduce anything. By now, you are all experts on this BCJ double copy. So now you are super familiar with all of these buzzwords of what is color kinematics duality, and you know about loops and going to 5 loops, and you know about supergravities and finite nets and super finite nets and the web of theories. But there is another aspect about double copy that has received a lot of interest in the last few years, which is exact solutions. So what exact solutions? Of course, we go with the coolest, which is black holes. So this was first studied in this paper by Ricardo Monteiro and Donald O'Connell and Chris White, who's my supervisor from the PhD. And in 2014, they came up with this relation between certain solutions, exact solutions in GR, and corresponding exact solutions in gauge theory. In this case, will be a linearization of Yang-Mills, which effectively looks like EM, like Maxwell equation. And they argued that this is an analogous story to the BCJ double copy. So just to help me with that statement, I brought some colors. So the idea is that you have, in the case of the BCJ double copy, you have an amplitude in gauge theory, and you have an amplitude in gravity. And you have a piece that carries the kinematic information is that N from numerator, and a piece that carries the color information, that's C. And then you obtain the gravity amplitudes by replacing the color with another copy of the kinematic information. On the classical solution side, they have a solution which will be very special. We will talk about that. But it will be of Kerr form, and this will factorize the graviton. And then we will have two copies of this vector, which is analogous to the kinematic information. And then they build a gauge field that satisfies this linearized Yang-Mills by taking some kind of analogy to the replacement that is given in the BCJ double copy. So this is now called the Kerr double copy because it relies on these Kerr ansatz. What it says is we have the metric, and then we split it. So we take out what is the background metric, which in this case will be Minkowski, and what is on top of that we call the graviton, is that h mu nu. Just to be very clear, this is an exact statement. This is not a linearization like what it's done sometimes in gravitational wave physics. This is just exact. And the Kerr ansatz is this factorization of the graviton as two copies of this vector, which is null and is geodetic, and one scalar function. So just a comment, in case you are into history of physics, I highly recommend that you go read this paper by Roy Kerr. That's called Discovering the Kerr and Kerr Metrics. Just because of the footnotes that this guy includes in this paper, it's worth it. But anyway, once we have this kind of metric that is in Kerr form, and we know that it is key that the vector, this vector appearing here, is null, because then the metric has this inverse. And again, these are exact statements. So when one does a linearized theory for gravitational waves, one finds something like this, but then there are things that are order graviton squared. In this case, because of the nullness of that vector, that is not needed. This is the metric exactly. So using this property of the metric plus the geodeticity, we will have a Ricci tensor which is linear in the graviton. And this occurs only for displacement of the indices. So one up, one down. And then we have this statement. Again, this is an exact statement. So the key property of these Kerr metrics is that they will linearize the Ricci tensor. Okay, so then what? We have this expression for the Ricci tensor, and we assume that there are stationary solutions. So all of the derivatives with respect to time, they vanish. So then we pick the components, so the 0, 0 components and the I0 components, and they are these two equations. So if we consider that R mu nu is 0, so that we have a vacuum solution, then we have these two equations, and we define these gauge theory fields, given as the product of just one instance of the vector times that scalar fields. And these guys become exactly the derivative of the field string tensor. So we can assemble this into the Maxwell equation. Sorry. So as we promised, starting from this metric, which has that Kerr form, then we can give a field that is a solution to a Maxwell or a linearized Yang-Mills equation. And they argue that this process is exactly analogous to the BCJ double copy. And it's a non-perturbative manifestation of the BCJ double copy. Okay, so they give some examples. And as we mentioned earlier about Schwarzschild and Kerr. So we start, we can see this explicitly. We start with Schwarzschild, and then the scalar field there is a spherical symmetry, so it can pretty much only look like that. And then for the vector, we have the same thing. And then we do this kind of single copy replacement. So there is the coupling constant, which is the same that BCJ does. And we replace 2 copies of the kinematic vector with only one. We leave the scalar, which is analogous to the propagators in the BCJ story. We leave that unchanged. And we replace the mass with the color charge. So what we obtain a field that, as we had said, will satisfy a linearized Yang-Mills equation. And what is this field that we obtain? This is in the same way that this is not the Schwarzschild form that one is used to. This will land on a gauge field that we don't know what it is. But after performing a gauge transformation, we can find that this is just like a Coulomb-like solution for a color charge, placed in the origin. Okay, so the next example that they give is this Kerr metric. So yeah, this is given in Kerr-Schild form, and this is actually the most natural way for Kerr. If you go back and read the paper that I recommended, they actually, when they were trying to derive Kerr, they came up with the Kerr-Schild ansatz. So this is pretty much the most natural form of the Kerr metric in words of Roy Kerr. And then, because it's already in Kerr-Schild form, we can take the single copy, as we learned in the past few slides, and we can interpret that solution as one in-gauge theory sourced by a rotating charge disk. Okay, so as SB said, this is an example-based field or formalism or whatever you want to call it. So next we say, okay, what other solution we know that might have a Kerr-Schild form and we can treat? And there are not that many really that one can play with. But turns out that if you look at taub-knots, which is a sort of generalization where you have now 2 parameters for the solution. One is the mass and the other one is called the knot charge. This is not spherically symmetric, but axially symmetric. This guy can be put not in Kerr-Schild form, but in what is called a double Kerr-Schild form. So instead of having the graviton factorized as 2 copies of the vector and the scalar, now we have 2 different vectors, 2 different scalars. And instead of having that nullness condition, which could be just k squared equals 0, now we have 1 for each of the vectors, and they are orthogonal to each other. This can be done either complexifying or going to a different signature. But now we have something that it's a double Kerr-Schild form. So following our intuition from the past, before that, the background here, this will depend on some parameters. So for example, here we have gamma, epsilon, and lambda. And this gamma is related to the angular momentum. So that's why we have Kerr taub-knots. And this lambda is related to the cosmological constant. So this is Kerr taub-knots de Sitter.
Andres, yep. I have a question. How is this background chosen? Like when you do normal Kerr-Schild,
yep,
it's Minkowski, right?
Mm-hmm.
So how do you choose that G with the bar?
Right.
I mean, classically.
Yes. So This actually comes from the old work by Jerzy Plebanski. So Plebanski studied this metric, and actually later he generalized to an absolutely general type D solution, which has even one more parameter. So he starts with an ansatz and he constrains, and then he gives something that is a general thing. Okay, then he shows that for certain choices of these parameters and some limits, this actually corresponds to tau naught. So we noted that this is Kerr tau naught de Sitter, and even Plebanski even gave the Kerr shield form in his old papers. So this is not something that we chose. This is how the solution behaves if you want to have a tau naught over in the Kerr shield form.
So how should I think of it? Like, I construct the right-hand side, like the one that's kappa with the phi and the psi, and whatever is left, that goes in the background. Is that?
Yes. So this is what you are gonna find if you insist on the solution being of Kerr shield form.
Thanks.
Yes, that's actually a good question, but this is just ad hoc so that this is of double Kerr shield form. So there is, as I said, this has several parameters. So there is the knot charge, and there is the mass, and these guys are different to this gamma and lambda. In the case, well, to gamma. In the case that if you turn off this n and m, you will have something that is flat, even if gamma is on. But okay, so let me just keep on going. So now that we have this double Kerr shield form, we can propose a single copy field following the same ideas as before. So we have this a mu and this given just as this taking one copy of the vector times the scalar, and it goes times a vector field, a color vector field, which this will trivialize because we will linearize the equation, and so we could ignore that. It's not that important. But we can see that this corresponds to a dione in electromagnetics. So, okay, going back to some question that was made a few hours ago. So what about core backgrounds? This is something that we studied. So as I mentioned, for tau naught, we already have a form which is over a de Sitter background. So you can do all of these replacements, and this will be a solution to the equations of motion, say to electromagnetism, over a core background. But the background is not dynamic. So this we did. There is our paper in 2017. There is a paper by Mariana Carrillo and Penko and Troden just 1 month later. But this is all in the context of classical solutions. And this is very stationary, so this is not really scattering. And just to show that this is still some active field, and there are some questions still trying to be answered. There is this paper which is 8 days old, talking about classical double copy in curved spacetime. But this is again classical solutions. So thinking about scattering, there are some papers by Adamo, Casali, Mason, and Nekovar, and they talk about scattering over core backgrounds, but they go to these specific backgrounds, which are plane waves. So they develop a formalism, and at 3 points that worked nice, and you can have a sort of double copy. But then when they try to go to 4 points, color kinematics is spoiled. But they say that although the duality is obstructed, the obstruction has an interesting constraint structure. So that was just picking up that question from a previous talk. Okay, so that was the Kerr double copy. It worked for Schwarzschild and Kerr, and then Kerr taught not the theater, and we studied in core backgrounds. We did some other things. I want to move now to the Weil double copy. This was introduced in this Type D Spacetime and the Weil double copy paper, which Donald and Ricardo Monteiro and Isabel and me, we presented a few years ago. So this is a double copy relation between the Weil and the field strength spinors. So there you have something which is gravity and is given as two copies as something that is EM, and there is some scalar there to balance some things. Okay, so just to set up some of the formalism, I will be talking about spinors. There is an alternate description. So usually when we go to school, we learn gravity in terms of tensors. But you can equivalently give a description in terms of spinors. This is something that the likes of Penrose use a lot. The name will come back. So we can transform from tensor indices to spinor indices using these Infeld-van-der-Waerden symbols. So basically, every time you have some vector, you just hit that with this symbol, and you obtain an object which carries spinorial indices. Just for completeness, I include how these symbols they can be understood in terms of the polymatrices, and yeah, it is important to have a Bern description of our fields to be able to use it like that. Okay, so we will be mostly interested in vacuum solutions, and when we have that, the Weil tensor, which is the object that we will be interested in, equals the Riemann tensor. So then we can focus on this Weil tensor. And if we hit it with the Infeld-van-der-Waerden object symbol enough times, we will have this Weil spinor. And it will happen that this will be split in this form, where we have these 4 index objects. And there are actually 2 of them. And one of them carries the self-dual. One of them carries is self-dual, and the other one is anti-self-dual. So it can be shown that one can go directly to this object, which is the one that was appearing in the double copy relation, by hitting the Weil tensor with this object, which is similar to the Infeld-van-der-Waerden. But anyway, too many questions just to say that we can translate to a spinorial formalism, and this will be the objects in which our Weil double copy will be stated. There is an analogous process that we do with the field strength spinor. So we start with the tensor, and then we hit it with this symbol, and then we have these 2 objects. One of them is self-dual, the other one is anti-self-dual, and we will focus on this one that we can obtain directly from hitting our tensor with these objects that are built in terms of polymatrices. Okay, so now we have all of the ingredients that we needed to state our Weil double copy. And this is, as I said, a double copy relation between the Weil and the field strength spinors. Okay, give me one second. there. So it will turn out that this kind of double copy is related to the Petrov classification of spacetimes. So I don't want to say much about that, but when we have a spinor that is symmetric in all of its indices, this will factorize as the product of one index spinors, so just spinors. And in the case of the vial, there will be 4 of them because there are 4 indices in the terms of field. In the case of field strength, there are 2 of them. So we can think, for the field strength, there are 2 options. They are either proportional or they are not proportional, they are different. In the case of the vial, there are actually more cases possible. So you can have all of them are different, or you have one that is degenerated and there are 2 copies and the other 2 are different, or you can have 3 of one and one that is different, or all of them are the same, or 2 and 2. In this case, turns out that very natural for the vial double copy are the N and the D types in the Petrov classification. Because if we are taking the square of the field strength spinor, if they are different, when you take the square, you have something that has 2 and 2. And if they are the same, when you take the square, you have something that has a degenerated principal null direction for 4 times. Okay. So we will, well, we focus on that paper on the type D spacetimes. And as I said a few minutes ago, Plebanski and Demiansky in the 60s or 70s, they studied this general solution for type D spacetimes. So they come up with something like that. They actually start with an ansatz and they start constraining, and then they say the most general solution that you can have will have this form, and it will have these parameters. And these guys, there are 4 of them. There is gamma, there is N, epsilon, and M. And this is because I turned off the cosmological constants. And I did that because the understanding of the spinorial formalism over curved backgrounds is a bit less developed than over flat backgrounds. So I want to focus here on things that have no cosmological constant. Actually, in the general solution, there is the cosmological constant. I just got rid of that. So I have now 4 parameters, M and N, epsilon, and gamma. And they will be related to the mass, the not charge, the angular momentum, and some acceleration. This relation is not yet direct. I will have something to say about that. But now we have a solution which is of type D and very general. Turns out that this Plebanski-Demiansky is of double Kerr form. So you can find an explicit change of coordinates that will take you to a form that is double Kerr. And then you will have some explicit forms. I am not that very concerned with them right now. So once we have that double Kerr, we say, okay, so then we can take a single copy. And the first thing that we will try after the success with previous solutions is saying, I will take this phi k and phi l. So put here some phi k and phi l. And if you go and check that, that is not a solution to Maxwell. So what happened that was okay before and is not okay now? So one thing that I said before is that we consider stationary solutions. Every example that we had seen before was stationary. And it was just in the right form so that everything ran smoothly. but not here. For this form, even being a double Kerr field, one can, well, if you take the naive single copy, that will not be a solution. So what we do is take this understanding, well, take an understanding in terms of the bile and the field strength spinor. So we know we can compute exactly what the bile is. So then we can have an idea of what the field strength spinor has to be in order to satisfy the bile double copy. And then we can look for a field that will give me this field strength spinor and will satisfy Maxwell equations. So we can solve this, and we can, and we say that this field will be the single copy of the general type D solution. Okay, so we say that this type D has these parameters which are related to mass and not charge, and angular momentum and acceleration. So it has to contain tau naught and even Kerr tau naught. So as I said, these metrics are contained, but one needs to work for them. So what one needs to do is rescale the metric that we already have. So we use this parameter L, and we rescale both the coordinates and the parameters in the theory, and then take this L goes to infinity. And then we recover tau naught. And if we apply the same rescaling to the single copy, we recover the solution that we have with the Kerr shield double copy. So then we have confidence in this single copy that we proposed, and we can go further. I say that one of these parameters is related to an acceleration. So what kind of acceleration? If we give this rescaling, this will give me something that is called the symmetric. This is a classic form of the symmetric, that alpha is related to a constant acceleration of a black hole. So in the limit case, alpha goes to 0. This is Schwarzschild. But in the general form, that belongs to an acceleration. And yeah, of course, if we just take it at face value, it will give it to me in some different coordinates. We have to find the change of coordinates to convince ourselves that we were on the right track. But then we do the same thing for the single copy, and that what we obtain is that this solution is a gauge transform removed from being linear Wishart, which is the potential for an accelerated charge, which is exactly what one would expect to be the single copy of an accelerated black hole. Okay, and then we can use this type D double copy. Well, yes, the Weyl double copy, to examine other solution which is of type D that had been of our interest, which is Eguchi-Hanson. This Eguchi-Hanson is an analogous of the, it's a gravitational instanton. So it's the analogous solution to what would be an instanton in gauge theory. So the first time I tried this, I computed what is my self-dual piece of the Weyl spinor, and I got 0. So I said, oh, this is not working nicely. So I talked to Ricardo Montero, and I say, hey, this is broken. It gave me 0. And he said, well, of course, did you check the anti-self-dual? And I say, oh no, I didn't think of that. So I go and check it, and this doesn't vanish. In the previous cases, because we were working with real solution, with real spacetimes, the self-dual and the anti-self-dual are conjugate to each other. So, but because Eguchi-Hanson is a complex solution, that will no longer be the case. So, moreover, this is known for being a self-dual, a solution to the self-dual equations in gravity. So it has to be that the vial carries only either the self-dual or the anti-self-dual part. Okay. So I forgot to say it. This is already in Kerr form. Yes, there is a background here. This is just an Euclidean spacetime. And this is in terms of one parameter. So here I have something like like the scalar field in front of this vector, which is a square. So I can propose this single copy, just like phi k mu, and then I go and check what is its anti-self-dual, because the self-dual part of the field strength spinor will vanish, and I obtain this guy. And this fits perfectly on my Vial double copy picture. So if I take the square of this, I obtain exactly that. And life is good. Okay, so we say that this Vial spinor will factorize, and because this is a type D, there are two copies of each of the two different spinors that define the null directions. So I know it will have two A's and two B's. And now, in the previous slide, we took this square root, which is like AB. And if you do that square, that gives you AB, AB. But we could also have taken something different. We could have said, what if we take this, one of them that goes like AA and the other that goes like BB? When I take my product, this is the Vial double copy again, this will still reproduce that C. So what happens there? If instead of taking the F, I take this M is for mixed double copy. Then what I find is that these are my field strength spinors. And actually, when we did this paper, the first time we studied the Eguchi-Hanson, it was with a very different approach. So coming from the self-dual equations, like Plebanski, the Plebanski equation, what one does is one starts with this scalar function, which is called a principal function, and then acts with a differential operator. And if you act once, that gives you the gauge field. And if you act twice, that gives you the graviton. And both of these guys satisfy self-dual equations. So this was the way that that we act, that we approached that problem, and we argued that this is the way to talk about self-dual solutions and double copy. Self-dual classical double copy, we call it. And if we do this, we actually land in one of these from the mixed double copy. So what we had before actually have taken us to this kind of solutions. Of course, because we know that there are two different, we knew that there had to be another differential operator, which we call K mu prime there, that is directly obtained from this guy just doing some switch of coordinates. And this produces the other field strength spinor that we can take as product to reproduce our Eguchi-Hanson. So in terms of this Vial double copy, we have learned that we can take actually different factorizations. And maybe we can put together guys which have different decomposition for the principal null directions to generate solutions that are not of type D or N. And this is something that Chris White, for example, is exploring with his tutorial approach to double copy. Yeah, just one comment about that. If we take one of these m's and just square it, what we would have produced is a type n solution instead. Okay. So are there any questions to this point?
I have a question.
Yeah.
I know the Iguchi-Hansen metric is in a Euclidean space, and asymptotically it looks like S3 mod Z2. So there's antipodal identification as you go out.
Mm-hmm.
What does that mean for the gauge solution? Is there any antipodal identification when you go way out in the gauge case too?
It's difficult to interpret those kind of global properties of the space-times. They are difficult. Well, I don't know if they are difficult. We haven't been able to study them using classical double copy. That was kind of actually the motivation to study the topological features of space-times. But for example, when we did this single copy, we landed on something that is EM, and EM will give trivial topology. So one of the things that we need to do is come up with a prescription to go to something that is non-abelian, and then we could try to really study the topological properties of what happens in gauge theory. But short answer is, because this took us to EM, then EM is topologically trivial, so I cannot do statements about that.
So is that a picture of the EM solution over there on the right? I'm just also trying to just get some more insight into what it means.
No, that's nothing.
Yeah. Okay. So
yeah.
Do you have pictures of the EM solution in any form, or magnetic and electric fields?
Yes. In the paper, they are in the paper. We can discuss them offline.
Yeah, sure. Thanks.
Any other question?
Yeah, I have one, but the thing is that I lost my internet connection, so I lost the part where you said something about the single copy. So
yeah, you can ask, and I can repeat, or that's okay.
I guess it kind of sounds like it was Lance's questions as well. So the question is, what is the single copy of this? What's the?
Well, I can tell you there are two single copies. So one of them is what we would have obtained with the Kerr shield form, which is this guy, and the other one is what we would have obtained with the different factorization and the mixed Weil double copy, which is like a differential operator acting on the principal function. This is the one that we have that we studied a bit more in the paper. It will look like a dipole in an Euclidean space.
Cool, thanks.
In the end, it has trivial topology, yeah, which is what we were most interested in, but yeah. Good. Any other question? Okay. So I guess I will. Yeah. So I will just take a break to reflect on what happened in the last year. So last year we got to meet in Mexico City in Colegio Nacional. So as Lucia said earlier, it was a really nice reason to visit Mexico, although I was there for like 24 hours or so, in part because less than 6 days later, I became a father, so I didn't have time to be in Mexico City. Of course, that was a very different world. So Susana Distancia was nowhere to be found in that picture. We didn't know. But we know what happened later. There's a pandemic, and we all moved to Zoom space. We are wearing masks, and things got way worse before getting a little better. But now we have vaccines. So anyway, life is looking better. But now is now. So this is where we are now. And if I zoom in on the title, it says new trends on QFT. If I zoom in even more, it says new. So let's talk about something new. Not by me, by the way. So there is this recent paper by Montero and collaborators, Codascar, Squared, and Peinador, Veiga, and Pope. And they do a similar story to the one for the type D, but in this case for type N. And this is important because the type N vacuum solutions, they are those that describe the radiation region of gravitational systems. So they have this paper by a double copy for gravitational waves. And they say that every solution of type N should be describable as a double copy of a Maxwell field. So in terms of the Weyl tensors, of the Weyl spinors. Other cool thing that happened in the last 14 months, since the last time that we met in person, are these papers. So there is this from Navier-Stokes to Maxwell via Einstein. This is Cindy Killer from ASU, Arizona State, with students Tucker Manton and Nikhil Monga. And they have this very interesting story about fluid gravity duality, which gives us a Navier-Stokes equation. And then, because there are some gravity solutions that are dual to these fluid systems, then they can study them. And they find that there are some type D and type N of these kind of gravitational duals. So they can study what the single copy in the sense of Weyl is for these solutions. And they found some solenoid gauge field. That was really cool. And even cooler is that this idea of relating Navier-Stokes to the double copy happened as well in a very different context in this paper by Clifford Chung and his student James Mangan. So this is called Scattering Amplitudes and the Navier-Stokes Equation. Again, very different approach. This is a more bootstrappy, like amplitudes bootstrap program, and they do the analogous, the analogous thing with some Navier-Stokes equation. But then they showed that you can have a sort of classical double copy. So, and the solutions for this, this is the non-abelian Navier-Stokes equation, and this is the tensor. So it has one extra index because it's like the double copy, it's like gravity, the tensor Navier-Stokes equation. And they say that this relation is almost identical to the Kerr field double copy. So two papers in the last year that relate the Navier-Stokes to classical double copy. And also one paper that was mentioned earlier in the day, this paper by Chris White that talks about a twistorial foundation for the classical double copy. And what he says is that the Weil double copy can actually be derived from twistor theory. And this is based on this object, which is called a Penrose transform, which relates objects in twistor space. So this twistor function, by doing this kind of contour integral, it relates it to some space-time fields. So the idea here is that from a very natural description in twistor space, one can obtain exactly the relation for them for the Weil double copy. Now that Penrose transform is limited to linearized solution, but of course he says in his paper that most of the things that we have seen, because they are very related to the Kerr-Shield ansatz that actually linearizes the Ricci tensor, they are sort of linearized solutions to gravity. So that's why he's able to give a description for most of the examples that we know and love, but still a description that is nonlinear is still needed. So I can summarize now. So there are many incarnations of the classical double copy, both in a perturbative sense, like SB and Alfredo described, and also in non-perturbative contexts, like this talk. So among the exact descriptions, we have the Kerr-Shield and the Weil double copies, and we have seen some cool developments in the last 14 months, counting from the first meeting in Mexico City, like a paper describing this for the type N solutions in the Petrov classification, which include gravitational radiation, making it very, very important. And also these relations to the Navier-Stokes equation. So a fluid, a description of fluids. And there is this twistorial approach from Chris White. So that's it from me. Thank you. Do you have any questions?
Thank you very much, Andres. Very, very nice talk. So we have time for questions, comments for Andres.
I have one.
Yeah,
go ahead, please, Daniel.
I think you didn't mention this, but it's kind of new. I mean, it's not that old, but I've seen that there's, I mean, I've recently seen that there's a relation between like old generating or classic generating transformations and electromagnetic duality with the double copy.
Yep,
Could you comment on that a bit? Because for me, that's new, like yesterday new.
Yeah. So this starts with a story. Okay, you mean like the papers by Donald O'Connell and
there's one, yeah, the one I'm referring to.
And there's also David Berman with people in Queen Mary and okay. So the way I saw this, it starts with the transformation from Schwarzschild to Kerr, and that is obtained via the Janis-Newman shift. So the statement of that is that in the right variables, you can obtain Schwarzschild simply by shifting, like doing a complex translation in one of its variables, right? So by being complex and adding a parameter, which is like A, which is like angular momentum, then that gives you Kerr. That's the first thing. And this appears in a paper by, okay, that was known in many years ago from this Janis and Newman, but it was thought like just a curiosity. So then, based on this idea of minimal coupling that Alfredo described in depth during his talk, and he says how you obtain this exponentiation and that relation between that you have actually between Schwarzschild and Kerr is already present, and it's very clear in terms of minimal coupling amplitudes. So in that paper by Donald O'Connell and Yutin Huang and Nimar Kani-Hamed, they talk about this relation in the classical form, and also how this is very transparent in terms of minimal coupled amplitudes. So, and then using the KMOC formalism that translates amplitudes to observables, they give some evidence in terms of the impulse of a particle moving in a geodesic over that spacetime. So, and that's the story for going from Schwarzschild to Kerr. Then in an analogous, well, in a similar process, there is another complex transformation that will take you from Schwarzschild to tau naught. And that transformation is related to the electric magnetic duality. And this is something that like 3 groups did at the same time, right? So there is Donald and Yuting and Cole. I don't know if it's Yuri Cole or Barack Cole. And there is another by David Berman and people. So I can tell you a bit more about the one with from Donald, because I've read that paper. But it's similar. It's just another complex transformation that will take you from Schwarzschild to tau naught. And they actually establish this web of theories that go from Coulomb and then double copy to Schwarzschild, and complex transformation to tau naught, or complex transformation to Kerr, and you go all the way from Coulomb to Kerr-Newman. So you have all that go of theories, and that is based on writing the things in the right variables, in the right form, and then taking complex transformation. And for example, then they use this KMOC formalism to give evidence about that by studying the impulses of particles moving in those geodesics. But so part of the reason why I'm not talking about this is because that becomes non-perturbative when you do the link to observables. I mean perturbative. So they only do it to first order. And I was thinking of including that in the talk, but then I already had too many subjects. I didn't know if I was going to have time, but yes, that is new and that is very interesting. And for example, this idea of applying like a Janis-Newman shift to higher orders in spin and in G, it's very attractive, and it might have the applications to gravitational wave physics, like what Zvi was talking about, or Alfredo, a bit more formal. Yeah, so.
Cool, thanks.
Anyone? We have time for another question.
I have just a very superficial comment that the paper of Demiansky-Plebansky,
Yep.
I think was the most cited paper in Mexico. I mean, made in Mexico, not necessarily by Mexico.
Yeah, so Plebansky was in Simvestab, which is this institute in Mexico City. It's like an institute for advanced, well, center for advanced resurrection studies, something like that. I think he fled Poland at some point, and then he stayed in Mexico forever. And he was kind of God in that institute. So he was a very influential person in Mexico for a long time. If you go to that institute, everything is named after him. He was a really smart guy, and he was a very hardworking guy. They say that he was in the office like 16 hours a day, and then he was he went home and he kept working. So, but he founded a good school of general relativity in that institute. So the impact is still felt. Yeah. I guess that's why. Oh well, yeah. You say paper made in Mexico, yeah.
Okay. If there is no other question or comments, let's thanks very warm thanks to Andres for this very nice talk, and we hope to see you again. We know that you are living soon in the US, but we're still in touch with these Mexicans abroad. And thank you very much for being here. And I think that I personally like to thank to everybody for this meeting. Also my fellow colleagues, Lorenzo, Mario, for organizing this, Olga, for Brian also, for organizing this meeting. This would be not possible to do it without your help and your support, even if it is in Zoom, but you need hard workers with you to make this meeting. So I don't know, maybe Lorenzo, you want to make close comments and do this?
Well, maybe I'll just add as you said, we thank the speakers that have supported us with his time and knowledge. It's very, very interesting, even after their talks, the questions of them. So we really appreciate that, and we hope that when things are better, that we can have them here again, and we'll have a nice lunch and a good tequila, and we will have a nice time, because we are survivors of this difficult time. As you said, I also thank you, Roger, and Olga, Brian, for all the support, even emotional support to continue doing this. I was a bit nervous because I'm teaching online this semester, and then I get distracted very easily, the students. So I thought it would be very long, about half a day, but actually it turned out very well. We pay attention to the talks, and the format is the best that we can do, but it's not that bad at all. So I hope that the students enjoy the talks as much as I and as we. And well, we hope that we will keep in touch, and that next year we will have a school on quantum field theory, amplitudes, and gravity. So thank you very, very much, and have a nice weekend, everybody.
Yeah, thanks a lot, Lorenzo, Roger, Mario, for putting all this together.
Thank you, Professor.
Great.
Next year in Mexico.
See you. Yep.